Hello there, and welcome to Science for Sleep, where curiosity gets comfortable and the universe is kind enough to whisper instead of shout. Tonight, we're exploring a question so ordinary that it can hide in plain sight, and so enormous that it reaches from the smallest atom to the largest galaxy. Why is everything in the universe moving? It is one of those questions that can seem almost too simple at first. Things move. Of course they do. Cars pass by, clouds drift overhead, tea swirls in a cup if you stir it, and socks mysteriously migrate to places no laundry basket can explain. But if we pause for a moment and really look, the question becomes far stranger. Why should anything move at all? Why does the moon circle Earth instead of hanging in place like a decorative lamp? Why does Earth rush around the sun at tremendous speed while politely pretending to be still beneath your feet? Why do stars orbit galactic centers? Why do galaxies themselves drift through expanding space? Why do particles vibrate, electrons dart, and even the air in your room bustle invisibly around you? And perhaps most curious of all, why has motion never seemed to stop? Before we wander further into that mystery, I'd love to know where in the world you're listening from tonight and what time it is in your corner of things. Maybe it is late evening. Maybe dawn is beginning to gather itself outside your window. Maybe rain is tapping softly nearby. Wherever you are, I'm glad our paths have crossed in this moving universe. If you find these gentle journeys soothing, interesting, or simply a pleasant companion while you wind down, I'd be ever so grateful if you liked the video and perhaps subscribed. It helps this calm little signal travel outward to others who may need a quiet place to land. Now then, get comfortable. Let your shoulders loosen. Let the day begin to step back a little, because tonight while you rest we're going to examine something remarkable. You may feel still right now. Perhaps you're lying in bed. Perhaps you're curled into a chair. Perhaps you've settled beneath a blanket with the full intention of learning something fascinating for 5 minutes, and then accidentally waking up 3 hours later with autoplay asking difficult questions about your life choices. Either way, you may feel motionless. Yet even in this moment, you are moving in more ways than intuition would ever guess. The room around you is attached to Earth, and Earth is rotating. At the equator, that spin carries the surface of the planet at roughly 1,670 kilometers per hour. If you live farther north or south, the speed is lower, but still impressive enough that if it were printed on a treadmill, most people would politely decline. At the same time, Earth is orbiting the Sun at about 107,000 kilometers per hour. Meanwhile, the Sun itself is travelling around the centre of the Milky Way galaxy at roughly 828,000 kilometers per hour. And the Milky Way is moving too, drawn by gravity through a cosmic neighbourhood full of other galaxies, clusters, and structures too large to picture comfortably before bed. So even now, while you rest your head, and perhaps consider not doing any of those speeds personally, you are participating in several layers of motion at once. Stillness, it turns out, is often just motion that feels smooth enough to ignore. That idea alone changes how we see everyday life. When you sit on a train that glides steadily forward, it can feel stationary until you look out the window. If the ride is smooth, your body adapts. You sip your drink, check your phone, wonder whether anyone has ever truly understood platform signage, and forget that you are racing across the landscape. Motion without jolts becomes invisible. The same thing happens on Earth. Our planet moves with such consistency that our senses do not complain. There is no constant lurch, no rattling handle, no conductor announcing that we will soon arrive at Tuesday, so we experience ourselves as still. This raises a subtle but powerful truth in physics. Motion is relative. To ask whether something is moving, we usually need to ask, moving compared to what? You may be still relative to your bed. Your bed may be still relative to your room. Your room moves with the house with the land with Earth, Earth around the sun through the galaxy, and so on. There is no obvious cosmic sofa where the universe itself is sitting quietly. For a long time, humans naturally assumed that the ground beneath us was fixed, and the heavens moved around it. That made emotional sense. The floor seemed trustworthy. The stars did all the wandering. Yet science gradually revealed something more humbling and more interesting. We were moving too. We had simply mistaken familiarity for stillness. That happens often in life, and not only in astronomy. We assume habits are permanent because they are regular. We assume routines are stable because they repeat. We assume we are standing still when in truth we are changing gently all the time. But back to the cosmos, where the stakes are slightly larger. Why does motion persist? If you slide a book across a table, it slows down and stops. Everyday experience seems to suggest that movement naturally fades away. Push something, and unless you keep pushing, it comes to rest. That seems sensible. It also turns out to be misleading. The reason the book stops is not because motion dislikes continuing. It stops because friction interferes. The table resists. Air resists. Tiny bumps and molecular interactions steal energy bit by bit until the motion fades. Remove those effects, and something surprising happens. An object already moving tends to keep moving. This principle, called inertia, became one of the great turning points in science. Galileo helped clarify it, and Isaac Newton gave it famous form. An object in motion remains in motion at constant speed in a straight line, unless acted upon by an external force. In plain language, movement does not need to be constantly fed. It often only needs to be left alone. That is deeply counterintuitive if your daily experience involves carpets, brakes, and furniture corners. But in space, where friction is scarce, inertia becomes obvious. A spacecraft can fire its engines briefly, then coast for immense distances. It does not need to keep trying every second. Once moving, it continues. The universe, in that sense, is efficient. Motion is not always something that must be created anew. Sometimes it is simply what remains when nothing stops it. This helps answer part of our question. Why is everything moving? Because once things begin moving, they often continue. Yet this only pushes the mystery backward one step. How did motion begin in the first place? That takes us to the early universe. As best we understand it, the universe was once in an extremely hot, dense state. Space itself expanded. Matter formed, energy spread. Tiny fluctuations became the seeds of future stars and galaxies. From those early conditions came streams of matter, collapsing clouds, spinning systems and growing structures. Motion was present from the beginning, woven into expansion, gravity, and the transfer of energy. There may never have been a grand cosmic moment where everything sat politely still, waiting for instructions. Instead, change and movement appear to be fundamental features of reality. Even the word universe can mislead us into picturing a finished container full of objects. But the cosmos is not a museum display behind glass. It is an unfolding process. Stars form and die, galaxies merge, planets migrate, atoms vibrate, light crosses emptiness for billions of years, space expands while gravity gathers. Everything is active. Even things we casually call solid are busy beyond imagination. Take the mattress beneath you, the chair beneath you, or the floor beneath that suspicious pile of clothes you keep meaning to sort. Solid matter feels fixed because atoms are bound into stable arrangements. Yet inside every material, atoms jiggle, electrons occupy restless quantum states, and thermal energy creates constant microscopic motion. Temperature itself is tied to movement. Hotter matter means particles moving more energetically on average. So if your tea cools down, that too is motion redistributing energy. If wind brushes a tree, if dust settles, if ocean tides rise, if your heart beats, if your lungs lift and fall, if thoughts travel through neurons, motion is there. We are not creatures occasionally interrupted by movement. We are organised patterns of movement. Even rest is a special arrangement of activity. That may sound dramatic, but it is simply practical. Life depends on circulation chemistry. Electrical signaling, metabolism, exchange. The moment these motions cease entirely, life does too. Perhaps this is why motion feels so natural to us. We're made of it. Yet there is another side to the story. If everything moves, why does the universe not dissolve into total chaos? Why do planets trace reliable paths? Why do galaxies hold together? Why does anything circle rather than scatter? That is where gravity enters, calm and persistent. Gravity does not merely pull things downward, despite what staircases may have led you to believe. It shapes trajectories, it bends paths, it gathers matter into stars, stars into galaxies, galaxies into clusters. Without gravity, the universe would be a much thinner and lonelier place. With gravity, motion becomes structure. Earth falls toward the sun continuously, but also moves sideways fast enough to keep missing it. The result is orbit. The moon does the same with Earth. This pattern repeats across scales, creating a cosmos of elegant compromises between falling inward and flying onward. And once you notice that, the sky becomes less like a still painting and more like choreography. The stars above are not pinned decorations. They are travelers. Some drift in groups, some race alone, some orbit companions. Some are being born in gas clouds right now. Others are ancient lights arriving late from events long finished. When we gaze upward, we're not looking at stillness. We are looking at distance hiding motion. That may be one of the most soothing lessons science offers. Many things that seem frozen are simply moving on timescales larger than our own. Mountains rise slowly, continents wander, forests shift, rivers redraw maps, stars orbit galactic centers over hundreds of millions of years. Patience often reveals motion where impatience sees none. If nothing is truly at rest, then what does still even mean? Look around the room you're in now. There may be a wall standing quietly nearby, a table keeping to itself, a lamp minding its own business, perhaps a cup on the bedside table, perhaps a book half read, perhaps a heroic pile of laundry pretending it is part of the furniture. Everything may appear settled, calm, and motionless, and yet none of it is truly still. Tonight, we continue with one of the most curious lessons science offers us. Stillness, the thing we trust so instinctively, is often an illusion created by scale, perspective, and the limits of our senses. That sounds dramatic, but it's also wonderfully ordinary. Take the floor beneath you. It feels steady enough that entire civilizations have built emotional confidence upon it. Floors are reassuring, they suggest certainty. You place a foot down, and there it is, dependable and flat, or at least trying its best. But the floor is moving, it rotates with Earth, it circles the sun, it travels with the solar system through the Milky Way. It moves with the Milky Way through a wider cosmic landscape. Even the tectonic plate beneath your region shifts over geological time, slow enough to ignore, fast enough to reshape continents given patience. So when you say, "I am standing still," physics gently replies, "Compared to what?" That question changes everything. In daily life, we judge motion relative to nearby things. If your chair stays in the same place relative to your room, you call it still. If your cup remains where you left it, assuming no cats are involved, it is still. If a parked car remains by the curb, it is still. These judgments are practical, useful, and perfectly reasonable, but they are local truths, not universal ones. The car is still relative to the road. The road moves with Earth. Earth moves around the sun moves through the galaxy. So the parked car is both motionless and moving, depending entirely on the frame of reference you choose. This idea is central to physics. There is no single obvious viewpoint from which all motion is measured. Nature does not hand out a cosmic parking brake. Instead, motion is relational. Imagine sitting in a smooth train carriage. You place a coin on the table. It does not slide. Your drink stays put. You feel calm enough to contemplate snacks. Inside the carriage, things seem at rest. Then you glance out the window and discover the landscape racing by. Which picture is correct? Both. Inside the train, the coin is nearly still relative to you. Relative to the countryside, it is moving rapidly. Neither description is wrong. They simply belong to different frames of reference. Earth is rather like that train, only with fewer ticket inspectors and more oceans. We live inside a smoothly moving system, so our senses adapt to its motion. We notice bumps, changes, accelerations, starts, stops, and turns. Constant movement, if steady enough, fades into the background. This is why you do not feel Earth orbiting the Sun. At roughly 107,000 kilometers per hour, Earth is moving fast enough to impress nearly anyone. Yet because that motion is smooth and shared by everything around you, your nervous system has no dramatic complaint to file. You, your pillow, your house, your neighborhood, and the nearest loaf of bread are all moving together. No relative jolt, no sensation. The same is true of Earth's rotation. Depending on latitude, you're being carried around the planet at significant speed. But because atmosphere, oceans, buildings, and people rotate together, it feels like stillness. We tend to detect differences in motion more than motion itself. That distinction matters. If an airplane cruises steadily, you may feel almost nothing. If it suddenly drops a little, everyone becomes deeply philosophical. It is acceleration, not steady speed, that announces itself to the body. So stillness often means not no movement, but no surprising change. That is already enough to make everyday life more interesting, but we can go further. Even objects that remain fixed in place relative to their surroundings are not truly still internally. Take a wooden table. It appears solid, quiet, and calm. Yet at the microscopic level, the atoms inside it are in constant motion. They vibrate around equilibrium positions, jostled by thermal energy. Electrons occupy dynamic quantum states. Bonds flex subtly. Nothing inside the material is frozen in the common sense of the word. Temperature itself reveals this hidden restlessness. When matter is warmer, the particles within it move more energetically on average. When matter cools, that internal motion decreases. But reaching absolute zero, the theoretical state where thermal motion is minimized, is extraordinarily difficult. And even there, quantum effects remain. So your quiet table is not quiet at all. It is a busy arrangement behaving politely enough to seem calm. The same goes for the walls around you, the fabric of your clothes, the glass in a window, the metal in a spoon, the springs in a mattress, the keys on a keyboard that have endured too much. Everything solid is activity organized into stability. That phrase may be worth lingering on. Activity organized into stability. Many things we call still are not inactive. They are balanced. A spinning bicycle wheel can remain upright because of motion. A planet can maintain orbit because gravity and velocity balance. A heart maintains life through rhythmic motion. Even standing upright requires constant muscular adjustments so subtle you barely notice them. Stillness, in many cases, is not the absence of movement. It is movement working so smoothly that it resembles rest. Consider your own body. If you're lying down now, you may feel quiet and still. Yet blood circulates through vessels. Lungs rise and fall. Nerves fire signals. Cells repair tissue. Hormones travel. Immune cells patrol. Countless chemical reactions unfold every second. Your body at rest is one of the busiest places you will ever inhabit. Sleep itself, often mistaken for shutdown, is an active biological process involving memory consolidation, hormone regulation, tissue repair, shifting brain states, and cycles of remarkable complexity. You do not become inactive when you sleep. You become differently active. This pattern repeats across nature. A forest may seem still from a distance. Yet sap rises, leaves angle toward light, roots exchange nutrients with fungi, insects move unseen, moisture evaporates, seeds drift, bark expands and contracts with temperature. A lake may appear smooth and quiet. Underneath, currents circulate, sediments settle, microorganisms feed, gases exchange with air, temperatures layer and shift. A mountain appears timeless, yet rock fractures, minerals weather, gravity pulls grains downhill, tectonic forces lift or lower the crust over ages. Stillness often belongs to eyesight, not reality. Our senses evolved for survival at human scales, not for perceiving atomic vibration or continental drift. We notice what matters immediately: predators, food, weather, social signals, stares in dim light. We are not naturally equipped to feel plate tectonics or detect molecular agitation while making tea. So the world appears calmer than it truly is. There is no insult in this. It is efficient design. If our brains constantly presented every hidden motion around us, daily life would become exhausting. Imagine trying to relax while fully aware of every dust particle, every air current, every microbial encounter, every rotational speed, every orbital path, and the precise wiggle of your chair's molecules. Most people would never finish breakfast. Instead, the brain simplifies. It builds a usable world, not a complete one. This is why illusion in science does not always mean deception. Often it means useful approximation. The sun appears to cross the sky. Useful appearance. Earth rotates. Deeper explanation. The ground feels still. Useful appearance. The planet spins and orbits. Deeper explanation. A table feels solid. Useful appearance. Matter is structured fields, particles, probabilities, and motion. Deeper explanation. Reality is often layered this way. One layer helps you live, another helps you understand. Now, there is an interesting historical note here. For much of human history, people naturally assumed Earth was fixed because it felt fixed. This was not foolishness. It was honest observation using available tools. When you stand on stable ground and watch the heavens move overhead, geocentrism has emotional advantages. Then astronomy, mathematics, and careful measurement slowly revealed a harder truth. Earth was moving, and we had mistaken our frame of reference for the centre of reality. Science repeatedly offers this humbling service. It reminds us that feeling central is not evidence of being central. And the lesson continues today. You may feel still because your current frame of reference is local and familiar. Shift the frame, and movement appears everywhere. Astronauts experience this dramatically. Orbiting Earth, they are in constant freefall around the planet at immense speed. Yet inside the spacecraft, objects float serenely. Motion and apparent stillness coexist. Likewise, passengers on a ship may stroll casually while the vessel crosses an ocean. A child can nap in a car while the highway streams beneath. A cat can ignore major transit events entirely, provided the seat is warm enough. Frames of reference shape experience. This leads to a deeper philosophical comfort. Many moments in life feel static when they are not. You may think nothing is changing because change is gradual. A skill is improving quietly. Healing is happening invisibly. Habits are shifting by tiny increments. Relationships deepen through small repeated acts. Understanding accumulates unnoticed. Some of the most meaningful movement in life feels like stillness while it is happening. Only later do we look back and notice distance travelled. Nature is full of that kind of motion. Trees grow too slowly to witness day by day. Coastlines alter grain by grain. Galaxies rotate over spans beyond human memory. Children become adults while parents are busy looking for missing shoes. The absence of obvious motion is not the absence of motion. It is often motion unfolding at a scale different from impatience. There is another subtle point. If absolutely everything in the universe moved together in exactly the same way, with no internal differences, no changing distances, no shifts relative to anything else, motion might become meaningless to detect. We know movement through relationships. This compared with that, now compared with before, here compared with there. Without contrast, motion hides. This is why the stars helped humans navigate. Relative positions changed predictably. Why clocks work, why music works, why walking works, why stories work. Change compared with change. Reality becomes visible through difference. So perhaps stillness is not a thing we find often in the universe. Perhaps it is a name we give to patterns where change is too smooth, too small, too shared, or too slow for us to notice easily. That is a gentler way to think about it. The world is not falsely calm, it is dynamically calm, balanced, layered, active beneath appearances. Settle in again, because now we arrive at one of the oldest questions hidden inside our larger one. If everything in the universe is moving now, then when did that movement begin? There is something very human about imagining a grand starting moment, a silent stage, darkness waiting patiently, absolute stillness holding its breath. Then, at last, a dramatic cue. Motion enters from the left. It is a compelling picture. It is also probably wrong. Modern science suggests that the universe did not begin as a quiet room where things were later switched on. Instead, motion, change, energy, and expansion appear to be bound up with the universe from the earliest moments we can meaningfully describe. There may never have been a cosmic pause button. That can feel difficult to picture, partly because our everyday experiences all have beginnings. A kettle starts boiling, a car begins rolling, a song begins playing. Even an argument about where to eat usually has a clear opening statement. We're surrounded by events that start after a prior state of not starting. So naturally, we ask the universe the same question: what happened before motion? Yet the deeper physics becomes, the more that question starts behaving strangely. Because when we speak of the early universe, we're not talking about something happening inside pre-existing space and time. We're talking about the emergence of the very stage on which events occur. And if time itself has an origin, then before may not mean what we think it means. That is one of the most unsettling and oddly soothing ideas in cosmology. There may not have been a long stretch of empty minutes before the universe began, any more than there is land north of the North Pole. The question points in a familiar direction, but the map may end there. Let us begin with what evidence strongly supports. The universe, as far as observations indicate, was once far hotter, denser, and more uniform than it is now. Over billions of years, space expanded, temperatures fell, matter formed structures, stars ignited, galaxies gathered, and planets eventually became places where listeners could ask excellent bedtime questions. This broad picture is known as the Big Bang model. Despite the name, it was not an explosion in empty space. It was the rapid expansion of space itself from an early hot, dense state. That distinction matters. When a firework explodes, fragments fly outward into surrounding air. The Big Bang was not matter bursting into a waiting void. Space itself expanded everywhere. There was no center where someone forgot to install warning signs. Every region we now observe was once compressed into a much denser condition, then spread out. So when did motion begin? In one sense, motion was present immediately in expansion itself. Distances between regions of space increased, energy shifted, conditions changed. The universe was dynamic from the earliest moments we can model. Stillness does not appear in the opening scene. Now, the first fractions of a second are among the most mysterious chapters in science, though I promise not to call them chapters, so let us call them very intense moments with poor lighting. At unimaginably early times, the universe was so hot and dense that our current theories become incomplete. General relativity describes gravity beautifully on large scales. Quantum mechanics describes tiny scales with astonishing success. But combining them fully under those extreme conditions remains unfinished business. Physicists call this frontier quantum gravity. which is a dignified way of saying we know a great deal and also we're not done. Even so, we can trace the story remarkably far back. As the universe expanded and cooled, energy condensed into particles. Matter and antimatter formed. Forces that may once have been unified separated into the distinct interactions we know today. Quarks later combined into protons and neutrons. Atoms eventually formed. Light travelled freely. Much later, gravity sculpted clouds into stars. Each step involved motion. Particles collided, scattered, combined, decayed, streamed, and interacted. Nothing in the picture resembles a frozen arrangement waiting to be animated. The earliest universe was energetic beyond common comparison. If you're tempted to imagine it as chaos, that is understandable but incomplete. It was not random messiness in the ordinary sense. It was highly structured by physical laws, governed by symmetries, probabilities, and relationships we continue to study. It was active, not careless. There is another clue hidden in the night sky. When astronomers observe distant galaxies, they find that most are moving away from us, and from one another on large scales. The farther away they are, the faster the recession tends to be. This discovery, first developed through observations by Edwin Hubble and others, revealed cosmic expansion. Run that film backward in thought, and galaxies become closer together. Go back far enough, and the universe becomes denser and hotter. That is how we infer the early state. We also detect a faint glow filling space called the cosmic microwave background. Ancient light released when the universe became cool enough for atoms to form and photons to travel freely. It is one of the strongest pieces of evidence for the hot early universe. This light has been travelling for billions of years just to quietly support cosmologists. Very considerate. Now, where did later motions come from? Why do galaxies spin? Why do stars orbit? Why are planets not scattered randomly? For that, tiny imperfections were essential. The early universe was remarkably uniform, but not perfectly so. Minute fluctuations in density existed, likely amplified from quantum-scale variations during an early period often called inflation, a brief episode of extremely rapid expansion proposed to explain several features of the cosmos. Those slight differences mattered enormously. Regions a little denser than average exerted slightly more gravity. They attracted more matter, becoming denser still. Over immense time, these seeds grew into stars, galaxies, clusters, and the large-scale cosmic web. So the graceful motions we see today may trace back to tiny wrinkles in the infant universe. That is a comforting pattern. Small beginnings can lead to magnificent structure. A minuter symmetry becomes a galaxy. A slight curiosity becomes a career. One bedtime question becomes 18 long videos. Now, let us consider a different kind of motion, momentum. When matter falls inward under gravity, it rarely does so in perfectly straight symmetry. There are always slight offsets, uneven pulls, irregular distributions. As clouds collapse, these irregularities can create spin. This is why rotating disks form around young stars. Material circles inward. Planets emerge from spinning disks of gas and dust. Galaxies rotate because matter gathered with angular momentum. The universe did not need to separately invent spinning later. Ordinary gravitational evolution plus initial conditions do a great deal of work. Much of cosmic elegance emerges from simple rules repeated patiently. And patience, to be fair, the universe has in abundance. There is a common misconception worth clearing gently. People sometimes ask what the universe expanded into. The answer may be, it did not need to expand into anything external. Space can increase its scale without requiring an outside container. Just as the surface distances on an inflating balloon can grow without tiny two-dimensional ants needing to locate an external center on the rubber itself. All analogies limp eventually, but that one helps a little. Likewise, asking what caused the Big Bang can be meaningful, But the answer may not resemble everyday causes. When a domino falls, another domino likely pushed it. But the origin of the universe may involve laws, boundary conditions, quantum processes, or concepts not yet fully understood. Expecting a familiar mechanical trigger may be like expecting a fish to explain mountain weather. Reasonable effort, wrong environment. Some models suggest universes can arise from quantum processes. Others imagine bouncing cosmologies where a prior contraction preceded expansion. Some propose eternal inflation spawning many bubble universes. Others remain cautious and say we simply do not know. That caution is honourable. Science is strongest not when pretending certainty, but when measuring it honestly. So did motion begin at a single instant? Maybe not in the everyday sense. If time itself emerged with the early universe, then asking when motion started may be like asking, what is east of east? The language works locally but strains at the edge. Yet within the observable history of our cosmos, motion is there from the start. Expansion, interaction, transformation, gravitational growth. Change appears primitive. Stillness appears secondary. That reverses our intuition. We often imagine rest as natural and motion as interruption, but cosmology hints the opposite may be closer to truth. Dynamic processes are fundamental. Stable objects are temporary islands formed within ongoing change. A star is a balance between gravity inward and pressure outward. A planet is sustained motion in orbit. An atom is structured energy and quantum behaviour. A living body is chemistry maintained far from equilibrium. Restful things are usually negotiations. There is something emotionally useful in that. Many stable parts of life are not static because nothing acts on them. They endure because forces remain balanced. Relationships, health, skills, communities, even peace often require active maintenance, not passive stillness. Nature agrees. Now imagine the early universe about 13.8 billion years ago. Not as a blast in darkness, but as a rapidly evolving whole, space expanding, temperatures falling, particles appearing and vanishing, matter gradually gaining the ability to form lasting structures. Light eventually set free. Given enough time, hydrogen clouds gather, stars ignite. Inside stars, heavier elements form. Stars die and scatter them. New stars rise with planets around them. Chemistry becomes richer. On at least one small world, oceans, atmosphere, geology, and time collaborate. Life emerges. Brains evolve. Questions appear. And one evening, someone comfortably wrapped in blankets asks why everything is moving. That continuity is astonishing. The motions of today are not separate from the first motions. They are descendants of them. Your body contains atoms forged in stars whose birth depended on earlier cosmic flows, whose roots extend to the young universe itself. You're not observing the story from outside. You are made of its consequences. Even the calm act of listening is part of a chain of motions billions of years long. There is no need for that thought to feel overwhelming. It can feel intimate instead. The universe did not merely start moving and leave you behind. It moved until eventually it could notice itself. Now that we've followed motion back toward the earliest universe, we arrive at one of the strangest and most elegant parts of the story. Some things move through space, but the universe also does something far more surprising. Space itself expands. That sentence is so familiar in popular science that it can lose its oddness. We hear it, nod politely and continue with our tea. Yet if we slow down and really look at it, the idea is extraordinary. We are used to motion meaning an object changes position inside a background that stays put. A bicycle rolls down a road. A bird crosses the sky. A spoon falls off a counter with impressive commitment. In each case, something moves through space while space itself seems unchanged. Cosmic expansion is different. It is not mainly galaxies racing through a fixed emptiness like marbles across a floor. On the larger scales, It is the distances between regions of space increasing over time. The stage itself stretches. This distinction matters because it changes how we imagine the universe. There is a natural temptation to picture the Big Bang as matter exploding outward from one central point into a giant empty arena. Then galaxies continue flying away from that centre forever. But observation suggests something subtler. There is no special centre in ordinary space from which everything flees. Every large region sees distant galaxies receding. Wherever you stand, it can look as though everything else is spreading away. That sounds impossible until we use one of the most famous analogies in cosmology. Imagine dots drawn on the surface of an inflating balloon. As the balloon expands, every dot sees other dots moving farther away. No dot is the centre of the surface. The expansion happens in the surface itself. Now all analogies eventually wobble, and this one has limits. The universe is not literally a balloon, and please do not wait for someone to pop it. Still, it helps illustrate how distances can grow without requiring a central explosion point inside the space. The universe can expand everywhere at once. That's already a gentle challenge to common intuition. We often ask, what is the universe expanding into? A fair question, and one asked by many thoughtful people. The surprising answer may be, it does not need to expand into anything external. Space can change its geometry, scale, and distances internally. Expansion describes relationships between locations within the universe, not necessarily growth into a surrounding room. We ask for an outside because rooms have outsides, boxes have outsides, houses have outsides, and even cupboards have outsides, though sometimes emotionally cluttered ones. But the universe may not be that kind of thing. It may be the totality of physical space we inhabit, not an object sitting in a larger warehouse. Now let us ask how we know expansion is real. In the early 20th century, astronomers studying distant galaxies noticed something remarkable. The light from many galaxies was shifted toward the red end of the spectrum. This redshift indicated that those galaxies were receding from us. More than that, the farther the galaxy, the greater the recession tended to be. This relationship became known as Hubble's law, associated with Edwin Hubble and other pioneers who helped reveal the scale and behaviour of the cosmos. In simple terms, distant galaxies are generally moving away, and the farther they are, the faster the separation increases. That is exactly what one expects in an expanding universe. Imagine raisins in rising dough. As the dough swells, each raisin sees others receding. More distant raisins separate faster because more dough lies between them and expands. Again, not a perfect analogy. Also dangerous if listened to while hungry, but useful. This expansion is not something we directly feel in daily life. Your room is not enlarging overnight. Your coffee mug is not slowly becoming a bucket. Your trousers are not victims of cosmology, despite certain seasonal suspicions. Why not? Because local structures are held together by stronger forces. Atoms are bound by electromagnetism, planets by gravity, solar systems by gravity. Galaxies themselves resist expansion internally because their own gravitational binding is strong enough on those scales. Expansion dominates mainly across vast intergalactic distances where matter is sparse and no local binding wins decisively. So the universe stretches on the grandest scales while homes, mountains, cats, and inconvenient receipts remain more or less the same size. This selective behaviour is one reason expansion can feel abstract. It does not rearrange your bookshelf. It rearranges the deep architecture of cosmic distances. Now, there is a number cosmologists use to describe the current expansion rate, the Hubble constant. Its exact value has been the subject of careful measurement and lively debate. Different methods have produced slightly different answers, creating what scientists call the Hubble tension. Which sounds like a yoga posture, but is in fact an active research puzzle. Some measurements based on the early universe, such as the cosmic microwave background, suggest one value. Measurements using nearby stars and galaxies suggest another. The disagreement is not enormous, but it is significant enough to keep many researchers busy and coffee suppliers optimistic. This is how science often progresses, not through dramatic declarations every Tuesday, but through precise disagreements that reveal deeper truths. Now let us consider what expansion means for time. When we observe very distant galaxies, we also look into the past. Light takes time to travel. A galaxy 1 billion light-years away is seen roughly 1 billion years younger than it is now, if such language can be used carefully. So the expanding universe becomes a historical archive. The farther we look, the earlier we see. Telescopes are not only instruments of distance, they're instruments of time. This means cosmic expansion has allowed us to reconstruct a biography of the universe. We see younger galaxies, earlier structures, ancient radiation, and clues to how matter assembled over billions of years. Without expansion, our picture of cosmic history would be radically different. There is another important twist. For a while, scientists assumed that although the universe expands, gravity should gradually slow that expansion. Matter attracts matter. Galaxies pull on galaxies. So perhaps the stretching should decelerate over time. Reasonable expectation. Then, in the late 1990s, observations of distant exploding stars called Type Ia supernovae revealed a surprise. The expansion is accelerating. That discovery was so significant it led to the 2011 Nobel Prize in Physics awarded to Saul Perlmutter, Brian P. Schmidt, and Adam G. Rees. Something appears to be pushing the large-scale universe apart faster over time. We call this unknown influence dark energy. Now, dark energy is one of those terms that sounds as though someone in a laboratory accidentally opened a forbidden cabinet. In reality, it is a placeholder name for a measured phenomenon whose underlying nature remains uncertain. It may reflect the energy of empty space itself. It may signal new physics. It may reveal that our understanding of gravity needs refinement. At present, we know it through effects more than essence, and that is acceptable. Many scientific concepts begin as careful labels for mysteries. Electricity was used long before fully understood. Gravity was described mathematically before its deeper geometry became clear through Albert Einstein. Dark energy may one day feel equally ordinary. For now, it remains one of the great unfinished sentences of cosmology. Let us return to the emotional side of all this. The universe expanding can sound lonely at first. Galaxies drifting apart. Distances increasing. Future skies emptier than present ones. And indeed, on immense timescales, distant galaxies beyond our local gravitational group may recede so far that their light can no longer reach us. Future astronomers, if any remain somewhere, may see a darker, quieter cosmos than we do. Yet there is another way to view expansion. Because space stretches, stars had room to form, galaxies to separate, chemistry to diversify, planets to emerge. Expansion allowed cooling. Cooling allowed atoms. Atoms allowed clouds, stars, carbon, oceans, biology, and eventually listeners trying to relax while contemplating space-time. A perfectly static, hot, dense universe would not have become this rich world of structure. Expansion made complexity possible. Distance is not only separation. Sometimes it is the room required for things to happen. That is true in life as well. Growth often needs space. Ideas need space. Recovery needs space. Relationships need breathing room. Gardens, music, thought, and sleep all benefit from a little expansion. The cosmos seems oddly sympathetic to this principle. Now, there is a subtle point worth appreciating. Expansion is usually very slow on human scales. The distances between galaxies are immense, and the rate becomes meaningful mainly across those vast spans. Nothing dramatic occurs in your bedroom because of it tonight. No ruler will suddenly misbehave. No lamp will flee the table. No biscuit tin will become unreachable by cosmological drift, though personal restraint may produce similar results. Yet despite its gentleness locally, expansion has transformed the entire history of everything. This is one of nature's favourite methods. Tiny rates applied consistently over immense durations create enormous consequences. Water shapes stone, roots split rock, habits shape lives. Space stretching quietly over billions of years reshapes the visible universe. There is no need for constant drama when time is available. Another common question appears here. If everything is expanding, why did the Milky Way and Andromeda Galaxy begin moving toward each other? Because local gravity can overpower cosmic expansion on smaller scales. Our local group of galaxies is gravitationally bound. Within such systems, mutual attraction wins. So while the larger universe stretches, neighbours can still drift together. This is an excellent reminder that broad trends and local realities often coexist. The global economy may do one thing while your bakery does another. Climate trends differ from today's weather. Cosmic expansion proceeds while two galaxies prepare an eventual merger. Scale matters. Expansion carries the universe outward on the grandest scales, quietly increasing distances between faraway galaxies. Yet if that were the whole story, the cosmos would be a thin and lonely mist, matter drifting apart without ever gathering into stars, planets, oceans, or the comfortable room you may be resting in now. Something else has been at work from the beginning, something patient, persistent, and astonishingly effective. Gravity. It may not feel dramatic in daily life. We speak of gravity most often when dropping keys, climbing stairs, or regretting the ambitious placement of an item on a high shelf. It seems like a downward force, useful mainly for keeping furniture honest. But gravity is far more than downwardness. Gravity is one of the great organisers of the universe. It gathers scattered matter into clouds. It compresses clouds into stars. It guides planets into orbits. It shapes galaxies. It bends light. It helps determine the large-scale architecture of the cosmos. Without gravity, motion would still exist, but much of the graceful motion we admire would not. No planetary years, no moons circling worlds, no stars burning steadily for billions of years, no galaxies turning in slow majestic patterns. Likely no life-arranging blankets and asking philosophical questions after midnight. So tonight, let us spend time with this quiet force. The first thing to notice is that gravity does not merely stop things from floating away. In many cases, gravity creates movement. That may sound backward. When people imagine motion, they often picture engines, pushes, kicks, or explosions. Gravity can seem passive by comparison, just a weighty nuisance that makes carrying groceries less glamorous. Yet gravity constantly turns stillness into trajectories. Drop a pebble, and gravity accelerates it downward. Release the moon from its orbital speed, and gravity would pull it inward. Let gas drift through space, and gravity can gather it into denser clumps. Give matter enough time, and gravity becomes an architect. This is one reason the universe is full of circles, ellipses, spirals, and arcs. Gravity bends paths. Now, for much of history, gravity was understood through the work of Isaac Newton. Newton described gravity as an attractive force between masses. Every object pulls on every other object. The more massive the objects, the stronger the pull. The farther apart they are, the weaker the effect. This idea was revolutionary because it united earthly motion and heavenly motion. The same principle that pulls an apple downward also helps guide the moon around Earth and Earth around the sun. That was an extraordinary moment in human thought. The heavens were no longer governed by separate mysterious rules. The sky and the ground belonged to one universe, and it worked beautifully. With Newton's equations, scientists could predict planetary motion, tides, trajectories, and countless other phenomena with remarkable accuracy. But centuries later, Albert Einstein offered a deeper picture. According to general relativity, gravity is not exactly a force pulling objects through space. Instead, mass and energy curve spacetime and objects move along those curves. If Newton's view is a tug, Einstein's view is geometry. A common analogy is a heavy ball placed on a stretched sheet, causing smaller balls to roll inward. The analogy has limits, but it helps suggest how mass changes the paths nearby objects naturally follow. Planets orbit the Sun not because invisible ropes yank them sideways, but because the Sun curves space-time around it, and planets move through that curved geometry. It is elegant, subtle, and almost suspiciously clever. Nature often is. Now, let us return to the theme of motion. Why does gravity keep things moving rather than simply making them crash together? Sometimes it does make things crash together. Gravity has no sentimental preference for neat arrangements. Asteroids collide, stars merge, galaxies interact in dramatic ways. The universe is capable of both elegance and mess. But when objects already have sideways motion, gravity can convert a straight path into an orbit. Imagine throwing a ball forward. Throw gently and it falls nearby. Throw harder and it travels farther before falling. Throw fantastically hard from a mountaintop on an airless world, and it falls around the planet instead of into it. That continuous falling around a body is orbit. The moon is perpetually falling toward Earth while moving sideways fast, enough to keep missing it. Earth does the same with the Sun. Satellites do the same with Earth. Orbit is one of the universe's favourite compromises, neither escape nor collapse. Motion guided by attraction. There is something calming about that. Many stable things in life are not fixed because nothing pulls on them. They endure because competing influences find balance, work and rest, freedom and commitment, curiosity and caution, gravity and momentum. Nature seems fond of negotiated stability. Now think of a young star forming inside a cloud of gas and dust. Gravity pulls matter inward. As the cloud contracts, it often begins to spin faster, much as a skater spins faster when drawing arms inward. The material flattens into a rotating disk. Within that disk, grains collide, stick, gather, and gradually form larger bodies. Pebbles become rocks, rocks become planetesimals, planetesimals become worlds. So gravity does not merely keep planets in orbit after they exist. Gravity helps build them in the first place. Your planet is not separate from gravity's story. It is one of gravity's long projects. The same is true for stars. When enough gas gathers under gravity, pressure and temperature rise in the core. Eventually nuclear fusion ignites. Hydrogen becomes helium. Light and heat pour outward. A star is born. That glowing object in the sky is not just a lantern hung in darkness. It is matter compressed by gravity until fusion begins. Gravity, paradoxically, helps create starlight. Even black holes, those famously serious cosmic objects, are products of gravity taken to extremes. When enough mass collapses into a sufficiently compact region, space-time curves so strongly that beyond the event horizon, escape becomes impossible. Black holes are often described dramatically, but they are also natural consequences of gravity acting without successful resistance. Nature does not always stop when we get nervous. Now let us scale upward. Galaxies themselves are held together by gravity. Hundreds of billions of stars orbit within the Milky Way because gravity binds the system. Galaxy clusters containing many galaxies are also gravitational structures. And here we meet an additional mystery: dark matter. When astronomers measured how fast stars orbit in galaxies, they found visible matter alone did not provide enough gravity to explain the motions. Something unseen appears to contribute extra mass. We call it dark matter, not because it is sinister, but because it does not emit light in ways we readily detect. Its nature remains uncertain, but its gravitational influence seems profound. So even our current understanding of gravity includes unfinished pages. Again, science remains strongest when honest about mysteries. Now, what does gravity feel like to you personally? you likely experience it as weight. Your body presses into a chair or mattress. Your feet meet the floor. Objects fall when dropped. Stairs negotiate from a position of confidence. Yet astronauts in orbit often appear weightless, not because gravity vanished, but because they and their spacecraft are in continuous free fall together around Earth. This is a lovely reminder that sensation can mislead. Weight and gravity are related but not identical experiences. Much of physics begins by separating what feels obvious from what is true. Gravity also shapes time itself according to relativity. Clocks deeper in gravitational fields tick slightly more slowly than clocks farther away. This effect is tiny in ordinary circumstances, but real enough that systems like GPS must account for it. Your phone's map works partly because engineers respect Einstein, a charming modern sentence. Without relativistic corrections, navigation errors would grow quickly. So gravity not only guides motion through space, it alters the flow of time. One force, many talents. There is another reason gravity matters emotionally. It gives us a sense of home. Downward is one of the earliest directions we learn. Balance, walking, reaching, climbing, catching ourselves when slipping, all depend on a stable gravitational environment. Creatures evolved under gravity's steady influence. Bones, muscles, circulation, posture and movement patterns all bear its signature. Even trees respond to gravity, roots growing downward, shoots upward. Gravity quietly shaped biology long before it shaped bedtime documentaries. Now imagine a universe without gravity. Matter spreads. No stars ignite. No planets assemble. No oceans settle into basins. No atmospheres remain bound. No galaxies form grand spirals. Light travels, particles move, expansion proceeds, but much of the rich structure we know never appears. Gravity is one reason the universe became interesting. Not the only reason, but a major one. And yet gravity is weak compared with other fundamental interactions on tiny scales. A small refrigerator magnet can defeat the gravitational pull of the entire Earth on a paperclip. This surprises many people. Gravity feels powerful because mass accumulates. Earth contains a great deal of it. Stars contain vastly more. Across huge distances, gravity dominates because it is always attractive and acts over unlimited range. Tiny weakness plus enormous persistence can become cosmic authority. Another useful life lesson, frankly. Now, there is a poetic temptation to call gravity destiny. Let us resist that slightly dramatic phrase and choose something better. Gravity is invitation. Matter invites matter closer. Paths bend. Structures gather. Motion becomes relationship. Planets circle stars. Moons circle planets. Galaxies dance past one another. Streams of gas fall inward and later shine. The universe does not merely scatter things, it also convenes them. And because gravity gathers while expansion spreads, the cosmos contains both separation and assembly at once. That tension creates much of what we see. Large scales stretch outward. Local regions condense inward. Galaxies emerge in between. Stars light up inside them. Planets form around those stars. Weather, geology, chemistry, and eventually sleepy listeners appear on at least one such planet. All because gravity kept matter from remaining alone. Once gravity begins gathering matter and motion already exists, the universe repeatedly arrives at one of its favourite solutions. Things circle, not always perfectly, not always forever, sometimes elegantly, sometimes chaotically, sometimes with the enthusiasm of a shopping cart wheel. But across the cosmos, again and again, objects fall into patterns of turning around one another. Orbits are everywhere. This may seem ordinary because we grow up with one enormous example. Earth goes around the Sun. Many people learn that early enough to mention it confidently long before they understand taxes, yet the deeper truth is much broader. Moons orbit planets. Planets orbit stars. Stars orbit galactic centers. Galaxies orbit within clusters. Binary stars orbit each other. Exoplanets circle suns we cannot see with the naked eye. Even small rocks, dust, and spacecraft join the choreography. The universe appears deeply fond of curved paths. Why? Because an orbit is what happens when inward pull meets sideways motion. That simple balance creates one of the grand, recurring patterns of nature. Imagine tossing a stone across a field. It moves forward while gravity pulls downward. Because the throw is modest and Earth is large, the stone lands quickly. Throw faster, and it travels farther before meeting the ground. Throw fantastically fast, and the curve of its fall can match the curve of Earth beneath it. It keeps falling, but the planet keeps curving away below. That is orbit. Continuous falling that never quite arrives. The phrase sounds almost philosophical, but it is precise. The moon is falling toward Earth constantly, yet moving sideways fast enough to keep missing us. Earth is falling toward the sun while moving sideways fast enough to keep missing it. Artificial satellites do the same around Earth. Many stable motions in the cosmos are forms of graceful missing. There is something unexpectedly comforting in that. We often imagine stability as standing still. Nature often achieves stability through motion. A bicycle remains upright more easily while moving. A top balances while spinning. A planet maintains its path by continuing forward while falling inward. Sometimes progress is what keeps collapse from happening. Now, not all orbits are circles. Children's books love neat circles because circles are tidy and friendly. Real physics is a little more varied. Most orbits are ellipses, stretched circles with one focus occupied by the central mass. This was described brilliantly by Johannes Kepler in the early 17th century, using the observations of Tycho Brahe. Kepler discovered that planets move in ellipses, sweep out equal areas in equal times, and have orbital periods related to their distances from the Sun. These laws were a triumph of pattern recognition before gravity itself was fully explained. Later, Isaac Newton showed that gravity naturally produces Kepler's results. This was one of science's elegant moments. Patterns first, cause afterward. It happens more often than one might think. You notice what works, then spend centuries explaining why. Now consider Earth's orbit. We often say Earth goes around the Sun once per year, and that is true enough for everyday use. But Earth does not move at a perfectly constant speed in a perfect circle. Our path is slightly elliptical, and our speed changes a little during the journey. When Earth is nearer the Sun, it moves faster. When farther away, it moves slower. This follows Kepler's second law. A line joining planet and sun sweeps equal areas in equal times. The universe, it seems, can be subtle while still being dependable. And no, the seasons are not caused by Earth being closer or farther from the sun. They arise mainly from Earth's axial tilt. A useful reminder that common explanations are not always correct simply because they sound plausible. Now let us widen the view. Many stars are not solitary like our Sun. A large fraction exist in binary or multiple star systems. Two stars may orbit a shared centre of mass, each responding to the gravity of the other. This centre of mass is called the barycenter. Even in our own solar system, planets and the Sun orbit a shared barycenter. Though because the Sun is so massive, that point often lies near or within the Sun itself. So it is not quite accurate to say planets move while the Sun stands still. The Sun wobbles too. Everything pulls on everything else. Nature rarely grants one-sided relationships. This stellar wobble has become one way we detect exoplanets. A planet tugging on its star causes tiny motions that astronomers can measure. From those motions, worlds unseen can be inferred. Whole planets discovered because their suns sway slightly. There is poetry in that, but also excellent mathematics. Some exoplanet systems are wonderfully strange. Hot Jupiters orbit close to their stars in just a few days. Some systems have tightly packed inner planets. Others contain giant worlds in eccentric elongated paths. Some planets likely circle two stars, giving sunsets that science fiction once enjoyed before astronomy became competitive. The universe is not obligated to copy our local arrangement. That is one of its charms. Now let us travel outward to galaxies. The Milky Way contains hundreds of billions of stars, each moving under the combined gravity of the galaxy's mass. Our Sun orbits the galactic centre roughly once every 225 to 250 million years. That means the last time our solar system was in this region of its galactic path, dinosaurs had not yet enjoyed their moment. We are all taking a very long ride. The centre of the Milky Way hosts a supermassive black hole known as Sagittarius, a star, around which nearby stars move rapidly. Astronomers tracked these stellar orbits to infer the black hole's mass long before direct imaging became possible. Even black holes reveal themselves through the dance of others. Again and again, orbit becomes evidence. Clusters of galaxies also contain orbital motions, though on grander and slower scales. Galaxies pass one another, merge, sling matter into tidal streams, and settle into new arrangements over immense timescales. The universe is dynamic at every level. Now, not every orbit is permanent. That is important. People sometimes imagine celestial mechanics as clockwork that, once started, continues unchanged forever. Real systems evolve. Tides transfer energy and angular momentum. The moon slowly recedes from Earth by a few centimetres per year because tidal interactions exchange rotational energy from Earth into the moon's orbit. Earth's day lengthens gradually over long times. So yes, ancient days were shorter. Dinosaurs lived with more days per year, though sadly no evidence suggests they used planners. Orbits can decay too. Satellites in low Earth orbit experience atmospheric drag and may eventually fall back. Binary stars emitting gravitational waves can spiral inward and merge. Planets can migrate through young disks. Chaotic interactions can eject worlds entirely. Motion remains orderly often enough to impress us, but not always enough to make promises. There is another subtle beauty here. Orbits allow environments where complexity can persist. Earth's orbit places it in a temperature range favourable to liquid water. The Moon's orbit stabilises aspects of Earth's axial behaviour. Regular cycles create seasons, tides, rhythms, and long-term climatic patterns that life has adapted to. Too chaotic a path might be harsh. Too unstable a star system, difficult. A reliable orbit can be a cradle. That does not mean Earth was meant to be this way. It means that where stable, favourable conditions arise, life has a chance to notice them. Selection often feels like intention from the inside. Now think of the psychological comfort humans derive from cycles. Sunrise and sunset, months, seasons, lunar phases, calendars, harvests, birthdays, the return of migrating birds, the first cold evening each year when everyone suddenly remembers blankets exist. We are creatures soothed by recurrence. Perhaps that is unsurprising in a world built by orbital regularities. Even our clocks echo celestial cycles. Days come from Earth's rotation, years from Earth's orbit, months loosely from lunar motion. Much of timekeeping began as astronomy with better paperwork. Now imagine a universe with gravity, but no sideways motion. Matter would mostly fall inward. Imagine sideways motion but no gravity. Matter would mostly disperse in straight lines. Combine both, and curves emerge. Many of nature's richest outcomes come from competing tendencies held together. Freedom and constraint, inward and onward, fall and flight. This is true in physics and not useless elsewhere. There is also humour in how common orbiting behaviour is in life. Pets orbit kitchens. Children orbit adults when asking difficult questions. People orbit refrigerators while claiming not to be hungry. Thoughts orbit unfinished tasks at 2 a.m. The word survives because the pattern is intuitive. Attraction plus motion. Now, why are orbits so efficient? because they conserve momentum while responding continuously to force. Instead of abrupt stops and starts, energy can remain in motion through repeating paths. The system evolves smoothly. Nature often prefers smooth accounting. This is why spacecraft use orbital mechanics so carefully. Missions can slingshot past planets, borrowing momentum through gravity assists. A probe visiting outer worlds may gain speed by passing giant planets in precisely planned trajectories. Gravity becomes steering rather than obstacle. The solar system itself is full of resonances, places where orbital periods lock into ratios. Some moons of Jupiter, for example, influence one another through repeated gravitational timing. These resonances can stabilize or destabilize systems depending on circumstances. Music has harmony, mechanics has resonance. Both involve timing shaping behavior. Now, perhaps the most calming truth of all is this: motion need not mean disorder. We often associate movement with chaos, noise, hurry, disruption. Yet much of the universe moves in patterns so reliable we navigate by them, predict eclipses centuries ahead, and launch spacecraft across billions of kilometers. Motion can be orderly, change can be rhythmic, movement can create home. As you rest tonight, Earth continues its orbit around the Sun. The Moon continues around Earth. The Sun continues around the Milky Way. Countless stars and planets continue their own paths unnoticed. You're surrounded by circles within circles, curves within curves, all proceeding quietly whether or not anyone applauds. If orbits are one of the universe's favourite ways to move, rotation may be another. Things do not only travel around other things, they turn on their own axes. Planets spin, stars spin, galaxies rotate, storm systems swirl, accretion disks whirl around black holes, asteroids tumble, moons turn. Even many particles possess an intrinsic property we call spin, though that particular kind is stranger than ordinary rotation and politely refuses to behave like a tiny spinning marble. The point remains, nature appears deeply comfortable with turning, and because spinning is so common, it can become invisible to us. Right now, as you listen, Earth is rotating. It completes one turn roughly every 24 hours, creating the cycle of day and night that quietly organizes much of life. Yet unless you are on a carnival ride of unacceptable design, you do not feel that rotation directly. The room seems still, the bed seems still, the cup on the table seems still, but all of it is turning together. That recurring lesson returns once more. Motion shared smoothly often feels like rest. Now let us ask the central question: why does everything spin? The short answer is that many things begin with even a tiny amount of irregular motion, and once turning starts, physics tends to preserve it. The longer answer is more satisfying. Imagine a vast cloud of gas and dust in space. It may appear calm from a distance, but perfect stillness and perfect symmetry are extraordinarily rare. Tiny random motions exist. Slight imbalances exist. One side drifts a little differently from another. Matter falls inward under gravity, but not with impossible perfection. That means the cloud often has some net angular momentum. Angular momentum is the measure of rotational motion. It is one of those phrases that sounds formal enough to wear a waistcoat, but the idea is intuitive. If something is already turning, it tends to keep turning unless acted upon strongly. This is rotational inertia. You know it from everyday life. A spinning office chair continues after a push. A top resists immediate stopping. A bicycle wheel dislikes sudden changes. Children discover this naturally. Adults rediscover it while assembling furniture incorrectly. Now return to our collapsing cloud in space. As gravity pulls matter inward, the cloud shrinks. When rotating matter contracts, it often spins faster. A familiar example is a figure skater pulling in their arms during a spin. With mass closer to the axis, the rotation speeds up. the same principle applies on cosmic scales. A broad, slow-turning cloud contracts into a faster spinning disk. Within that disk, a star may form at the centre. Planets may form farther out. Those planets inherit the motion of the original cloud. So the spin of Earth, the orbit of Earth, and much of the solar system's overall orderly motion likely descend from the rotation of a primordial cloud billions of years ago. Your sunrise is part of an ancient inheritance. That is rather lovely. Now, Earth spins once every sidereal day relative to distant stars, and about every 24 hours relative to the Sun because Earth also moves in orbit. This rotation gives us morning, noon, evening and night. If Earth did not rotate, life would be very different. One side would face the Sun continuously for long periods, depending on orbital circumstances, creating extreme heating, while the other side endured long darkness and cooling. Atmospheric circulation would be transformed. Daily biological rhythms as we know them would not exist. Rotation moderates conditions and creates cycles. Many living things rely on those cycles deeply. Plants track light, animals time activity. Humans create schedules, alarms, and occasionally ignore both. The turning planet sets the tempo. Now consider other worlds. Jupiter spins in under 10 hours despite being far larger than Earth. That rapid rotation helps flatten it slightly at the poles and contributes to powerful atmospheric banding and storms. Venus rotates extremely slowly and in retrograde direction, meaning opposite to most planets in our system. A day on Venus is longer than its year. That sounds like poor calendar management, but it is real physics. Uranus is tilted dramatically, effectively rolling around the Sun on its side. Nature does not mass-produce identical worlds, it experiments. Some spins come from inherited motion, others are altered by collisions, tidal forces, internal structure, and long histories of gravitational encounters. Now let us speak of the Moon. Our Moon rotates too, but it keeps the same face toward Earth. This is called tidal locking. It spins once on its axis in the same time it takes to orbit Earth, so it rotates and orbits together in matched rhythm. That is why we always see roughly the same lunar near side. The far side was not permanently hidden by malice, it was simply turned elsewhere. Tidal locking is common in the universe. Many moons are locked to planets. Some exoplanets close to their stars may be locked as well, with one hemisphere in perpetual daylight and the other in long darkness. Gravity over time can synchronize rotation. Patience is one of gravity's specialties. Now let us widen the scale. Stars rotate. Our Sun spins approximately once every 25 days near its equator, and more slowly near the poles because it is gaseous, not rigid. Different latitudes rotate at different rates. This differential rotation helps drive magnetic activity, sunspots, and the solar cycles that affect space weather. Even the star that warms your skin and lights your mornings is not static. It turns, churns, convex, and changes. Again, apparent steadiness hides internal activity. Some stars rotate astonishingly fast. Young or massive stars can spin at rates that flatten them noticeably. If a star spins fast enough, centrifugal effects become significant, making the equator bulge outward. Planets do this too, though more modestly. Earth is not a perfect sphere. It bulges slightly at the equator because of rotation. So yes, the planet is subtly wider around the middle from spinning. The universe contains many forms of rotational vanity. Now let us step outward again. Galaxies rotate. The Milky Way is a rotating disk of stars, gas, dust, and dark matter. Our Sun orbits the galactic center as part of that larger rotation. Spiral galaxies display sweeping arms not as fixed pinwheel blades, but as patterns moving through rotating material. Galactic rotation also revealed one of modern astronomy's greatest puzzles. Stars far from galactic centers often move faster than visible matter alone could explain. This evidence strongly supports the presence of dark matter, unseen mass contributing gravitational influence. Once again, spin becomes evidence. By watching how things turn, we learn what cannot be seen directly. Now, there is a subtle but profound principle behind all of this: conservation of angular momentum. In an isolated system, total angular momentum remains constant unless external torque acts. That sentence can sound stern, so let us translate. If something is spinning and no strong outside influence interferes, the turning motion must be accounted for. It can redistribute, speed up, slow down, spread among parts, but it does not simply vanish because someone lost interest. Nature keeps careful books. This principle explains why collapsing clouds spin faster, why ice skaters accelerate with tucked arms, why pulsars can rotate incredibly rapidly after stellar collapse, and why rotating systems can transfer motion through tides and interactions. Take a massive star nearing death. When its core collapses into a neutron star, the radius shrinks dramatically. Conservation of angular momentum can spin the remnant up to extraordinary speeds. Some pulsars rotate many times per second, sending beams of radiation through space like cosmic lighthouses. A star can die and become a precision spinner. The universe is rarely short on drama. Now consider Earth's own spin over time. It is not perfectly constant forever. Tidal interaction with the moon gradually slows Earth's rotation. Days lengthen by tiny amounts over long spans. Hundreds of millions of years ago, Earth's days were shorter. Ancient sunsets came sooner. The moon, meanwhile, slowly recedes from Earth as angular momentum transfers outward. One system slows while another expands. Physics balances accounts elegantly. Rotation also shapes weather. Because Earth spins, moving air and water experience the Coriolis effect. This influences large-scale winds, ocean currents, and storm rotation patterns. Hurricanes and cyclones organize partly through this rotating reference frame. Without planetary spin, global circulation would be profoundly different. Your climate owes something to turning. Even everyday actions borrow rotational principles. Opening a door by pushing near the handle rather than near the hinges uses torque. Riding a bicycle uses wheel stability. Throwing a ball with spin alters its path. A tossed pizza base in skilled hands becomes a public demonstration of angular momentum and confidence. We live surrounded by turning whether or not we name it. There is also a psychological comfort in cycles created by rotation. Morning returns because Earth turns. Night returns because Earth turns. Stars appear to wheel overhead because Earth turns. Much of timekeeping begins there. Rotation gives repetition, and repetition gives rhythm. Rhythm helps life feel navigable. Sleep cycles, meals, work days, migration, flowering, tides influenced by orbital companions, all depend partly on repeated motions. A universe that spins becomes a universe with clocks. Now perhaps the most calming insight is this. Rotation often emerges from tiny asymmetries amplified over time. A cloud need not begin with dramatic whirlpool motion. Just slight imbalance can grow into a disk, a star system, a galaxy. Small beginnings become grand patterns. This happens elsewhere too. A modest daily habit becomes expertise. A tiny change in posture becomes comfort. One quiet curiosity becomes years of learning. Nature does not always require spectacular starts. Sometimes it needs only a slight nudge and enough time. As you rest now, Earth turns beneath you. The sky outside changes, though slowly enough to seem still. The sun rotates. The galaxy turns. Countless worlds spin through their own mornings and nights. You're lying on a rotating planet inside a rotating galaxy in a universe rich with circles and whirls. By now, we have seen planets orbit stars, moons circle planets, worlds spin on their axes, and stars themselves turn while travelling around galactic centres. It would be perfectly reasonable to assume that somewhere, at some larger scale, the motion finally settles down. surely there must be a level where everything becomes still. A final layer of calm, a cosmic shelf where the universe sets things down and says that will do, and yet no. When we zoom outward, motion does not disappear. It multiplies. Galaxies move. Clusters of galaxies move. Groups of clusters drift through larger structures. Even the grandest visible patterns of the cosmos are not frozen architecture, but evolving arrangements in slow procession. Tonight, let us widen the frame until stars become grains and galaxies become dancers. Because the universe, at its largest scales, resembles not a static map but a long, patient ballet. Begin with our own home, the Milky Way. From inside it, the Milky Way can feel like the whole sky. Billions of stars, gas clouds, dust lanes, dark matter, and a central supermassive black hole all form a vast gravitational system roughly 100,000 light-years across. Yet the Milky Way is not standing still in cosmic dignity. It is travelling through space, influenced by neighbouring galaxies and the gravity of larger structures beyond. Our galaxy belongs to a modest gathering called the Local Group, a small collection of more than 50 galaxies bound together by gravity. Among its most notable members are the Milky Way, Andromeda Galaxy, and the smaller Triangulum Galaxy, along with many dwarf galaxies. These galaxies are not decorative neighbours politely holding position. They move around the shared gravitational landscape. Some orbit larger companions, some are being stretched tidally, some may one day merge, some have likely been captured over cosmic time. Even our local neighbourhood is active. Now consider Andromeda. It is approaching the Milky Way at roughly 110 kilometers per second. Not because it is rude, but because gravity draws our two large galaxies together despite the broader expansion of the universe. In several billion years, the Milky Way and Andromeda are expected to interact and eventually merge into a new larger galaxy. This sounds dramatic, and in a sense it is. But galaxies are mostly empty space. Direct star collisions are relatively unlikely. Instead, gravitational tides will distort shapes, rearrange orbits, trigger waves of star formation, and gradually blend the systems into a new structure. A galactic merger is less like two bricks colliding, and more like two swarms of fireflies passing through one another while music changes. Slow, vast, transformative. If anyone is around to watch from a safe planet at the time, the night sky may become spectacular. Now, step outward again. The Local Group itself belongs to a larger structure often, associated with the Virgo cluster, and broader regions sometimes described within the Laniakea supercluster. These names describe immense patterns of galaxies and clusters connected through gravity and cosmic geography. We use words like cluster, supercluster, filament, and void, because the universe on the largest scales resembles a web. Galaxies gather in strands and knots, with enormous relatively empty regions between them. This cosmic web is not static. Matter flows along gravitational gradients. Galaxies fall toward denser regions. Clusters interact. Structures evolve slowly over billions of years. The dance floor is larger than imagination, but the dancing continues. Now, let us pause for scale. A single galaxy contains hundreds of billions of stars. A cluster may contain hundreds or thousands of galaxies. The distances between clusters can span tens or hundreds of millions of light years, and still, gravity threads influence across these expanses. When humans say something is moving slowly, we usually mean a queue in a supermarket, or a download during unfortunate weather. Cosmic slowness is different. A galaxy cluster may take billions of years to complete a major interaction. Two galaxies may begin merging long before multicellular life exists on some distant world, and finish after civilizations rise and vanish elsewhere. The ballet is slow because the stage is enormous. That does not make it less real. In fact, some motions are easier to understand once we stop expecting haste. We often mistake speed for significance. nature frequently disagrees. Continents drift millimeters per year and reshape planets. Evolution proceeds through small changes and fills oceans and forests. Galaxies move over eons and redraw the heavens. Patience is one of the universe's most effective tools. Now, how do astronomers know galaxies move? Several ways. One is redshift and blueshift. Light from an object moving away is stretched toward longer wavelengths, becoming redshifted. Light from something approaching shifts toward shorter wavelengths, blueshifted. This is the cosmic version of hearing a siren change pitch as an ambulance passes, though with less paperwork. Andromeda is blue-shifted because it approaches us. Many distant galaxies are redshifted because cosmic expansion increases their separation from us. Within clusters, individual galaxies can be tracked statistically by their motions and distributions. Hot gas between galaxies emits X-rays, revealing cluster mass and dynamics. Gravitational lensing, where mass bends light, also helps map unseen matter shaping these motions. The universe leaves clues generously if one learns how to read them. Now there is an elegant tension here. On the largest scales, expansion tends to separate distant galaxies. Locally, gravity can gather them. So the cosmos does two things at once. It stretches broadly while clumping regionally, spread and gather, distance and assembly. This balance is why galaxies formed at all. If expansion alone ruled absolutely, matter would thin out too quickly. If gravity dominated everywhere, everything might collapse too readily. Instead, structure emerges between tendencies. Again, many fruitful things live in balance. Now let us speak of galactic collisions because they sound violent and are often surprisingly graceful. When two spiral galaxies interact, their mutual gravity can pull long tidal tails of stars and gas outward like luminous ribbons. Disks warp. Central gas may funnel inward, feeding bursts of star formation or active black holes. Eventually, the separate spirals may relax into a larger elliptical galaxy. Astronomers have photographed many such systems in mid-transformation. Some look like cosmic birds, rings, hooks, or luminous smudges in emotional conversation. Messy beauty on a grand scale. Our own galaxy has likely grown partly by absorbing smaller galaxies over time. Streams of stars still arc through the Milky Way as remnants of past mergers. Even large, serene things often contain histories of incorporation. Now consider the stars within a galaxy during all this. Most stars are so far apart that they simply continue on altered paths under the changing gravitational field. Their night skies would evolve, constellations would distort, neighbouring suns would brighten or fade, but individual, stellar collisions remain uncommon. Space, despite its crowded photographs, is mostly room. That fact alone surprises many people. Galaxies look dense because we see light compressed into images. In reality, the average spacing between stars is immense. The cosmos is generous with emptiness. Now there is another hidden actor in galactic motion: dark matter. When astronomers measure how quickly galaxies rotate and how clusters hold together, visible matter alone often appears insufficient. Extra-gravitational influence seems present. Dark matter, whatever it is, helps shape the ballet while remaining unseen directly. Many dancers perform in darkness. This is not poetic exaggeration. It is an observational puzzle. We infer mass from motion. That principle appears repeatedly in astronomy. Watch what moves, and you learn what exists. Now let us return briefly to ourselves. The solar system moves through the Milky Way while Earth orbits the Sun, while Earth rotates while you sit or lie apparently still. Add the Milky Way's motion within the local group, and the local group's motion toward larger structures, and you become a stack of motions nested inside motions. You're not on a stationary platform observing the universe. You're inside the choreography. This can feel dizzying if framed badly. Better to frame it differently. You're being carried by many stable motions at once. No effort required. No ticket needed. Now there is something emotionally reassuring in these immense slow dances. We sometimes fear change because we associate it with disruption. But much of nature changes continuously without panic. Systems adjust, drift, merge, reform, and continue. A galaxy can collide and still produce new stars. A cluster can evolve and remain coherent. Patterns can survive transformation. That is worth remembering beyond astronomy. Now imagine looking up from a future Earth-like world in Andromeda during its approach to the Milky Way. Over millions of years, our galaxy would grow larger in the sky. Dust lanes would sharpen. Tidal distortions would appear. New streams of stars would stretch across darkness. For countless generations, the sky itself would slowly become news. Yet each individual life might notice only subtle changes. Again, some of the greatest motions are visible only through patience. We have spent time among planets, stars, galaxies, and clusters, watching enormous things move across enormous distances. It is easy, after such grand tours, to imagine that motion belongs mainly to the large. Big objects travel, heavy bodies orbit, galaxies drift. Surely the tiny world must be calmer. Surely somewhere beneath all that visible activity, there is a layer of stillness holding everything together, and once again, the universe answers with a gentle no. When we turn inward instead of outward, motion does not vanish. It becomes faster, stranger, and more constant. The chair beneath you, the blanket around you, the air in the room, the cells in your body, the walls nearby, the stars above, all are made of atoms, and atoms are not little static bricks stacked neatly in silence. They are dynamic systems governed by forces, probabilities, energy, and ceaseless activity. Even what feels solid is full of motion hidden by scale. That may be one of the most useful themes in science. Reality often becomes busier the closer we look. Let us begin with the atom. For a long time, humans imagined matter as continuous stuff, perhaps divisible forever into smaller pieces. Later came the idea of atoms, once thought to be indivisible units. Then science, with its usual talent for making simple ideas more interesting, discovered that atoms themselves contain structure. At the centre lies a nucleus made of protons and neutrons. Around that nucleus are electrons, though not as tiny planets circling in neat miniature solar systems as old diagrams can misleadingly suggest. Electrons are better described through quantum mechanics as existing in states, orbitals, and probability distributions. They are not little marbles tracing tidy rings while wearing obedient expressions. The microscopic world is less clockwork, more subtlety. Still, one fact remains clear. Atoms are not still. Their components exist in energetic relationships. Electrons occupy changing quantum states. Nuclei can vibrate within molecules, bonds flex. Interactions occur continuously. Now consider temperature. When you touch a warm mug, you are sensing microscopic motion. The atoms and molecules in the mug have greater average kinetic energy than those in your cooler hand. Energy transfers through collisions and electromagnetic interactions until temperatures move toward equilibrium. Warmth is motion shared. Coldness is comparatively less motion. This is a simplification, but a useful one. So if you hold a cup of tea and feel comfort, you are partly feeling countless invisible jostlings passed into your skin. Science can be strangely intimate. The air around you offers another example. A quiet room may seem empty and still, yet the air within it is a swarm of molecules moving at hundreds of meters per second, colliding incessantly in all directions. They bounce from walls, mix with one another, carry scents, transfer heat, and exert pressure. Pressure itself emerges from these collisions. The calm atmosphere in your room is, at the molecular level, a riot of impact so balanced that it feels serene. Again, stability through activity. Nature uses that trick often. Now imagine a sealed perfume bottle opened briefly. Soon the scent spreads across the room. Why? Because molecules move randomly, Colliding and dispersing through diffusion, they wander from regions of high concentration toward broader distribution. No tiny manager directs them. Statistical motion does the work. Many large-scale behaviors arise from countless small movements without central control. Traffic, weather, crowds, economies, and internet comment sections occasionally follow similar principles, though with less elegance. Now let us look inside your body. Every second, molecules cross cell membranes. Oxygen diffuses into blood. Carbon dioxide leaves. Proteins fold and unfold. Enzymes catalyze reactions. Ions move across nerve cell membranes to generate signals. Muscle fibers slide microscopically to create movement. DNA is copied, repaired, read, and regulated. You're not a statue briefly animated. You are a process. Living systems maintain order by managing flows of matter and energy. Stop those flows entirely, and life ends. That means being alive is not a pause from motion. It is a highly organized form of it. Even rest is metabolically active. While you sleep, your brain cycles through stages. Memories are processed, tissues repair, hormones regulate, immune functions continue, and cells keep their busy schedules regardless of your opinion. Sleep is not shutdown, it is night shift. Now, we should pause on a common image people carry from school. Electrons orbiting nuclei like planets around the sun. It is understandable, visually tidy, and incomplete. Quantum mechanics replaced that simple planetary model. Electrons are described by wave functions and probability distributions. We can predict likely locations and energies, not classical little tracks. This means the hidden motions of matter are not always motions in the everyday sense of tiny balls rolling about. Sometimes they are changes of state, fluctuating probabilities, transitions, and behaviors that resist direct analogy. The small world is under no obligation to resemble billiards. That is worth remembering whenever reality feels strange. Nature did not design itself around human intuition. Now consider solids. A wooden table seems rigid and unmoving, yet the atoms inside it vibrate around equilibrium positions. Chemical bonds hold average structure in place, but thermal motion remains. Heat the table enough, and those vibrations increase. Cool it enough, and they diminish. Matter that feels firm is often microscopic motion constrained into pattern. Liquids behave differently. Their molecules remain close together but move past one another more freely. Gases freer still, spreading to fill containers. The states of matter reflect how motion and bonding interact. Solid, movement constrained. Liquid, movement cooperative. Gas, movement expansive. Again, physics loves balance. Now let us step deeper. Inside nuclei, protons and neutrons themselves are composed of quarks bound by the strong nuclear force, mediated by gluons. These are not tiny pebbles sitting politely inside a shell. Quantum fields fluctuate, particles interact, energy and confinement dominate the picture. At deeper scales, what we call particles are excitations of underlying fields in modern physics. That sentence can sound severe, but it means something beautiful. The universe may be less like objects floating in emptiness, and more like fields capable of localized ripples we experience as particles. So even the concept of a thing becomes dynamic. Matter may be structured activity. Now consider radioactive decay. Some atomic nuclei are unstable. Over time they may transform, emitting particles or radiation. This process can occur spontaneously according to probabilistic laws. Atoms can change identity, lead from uranium chains, helium nuclei from alpha decay, neutrinos streaming from reactions. Stillness is hard to find. The sun itself shines because nuclei move and interact under immense pressure and temperature, allowing fusion. Hydrogen nuclei combine into helium, releasing energy. The daylight that warmed your morning began as microscopic processes in a stellar core. Large experiences often begin small. Now let us talk briefly about Brownian motion, one of science's delightful confirmations of hidden activity. In the 19th century, Tiny pollen grains suspended in water were observed jittering randomly under a microscope. They were being buffeted by unseen water molecules in constant motion. This erratic dance helped support the atomic theory of matter. What looked like mysterious twitching was evidence of countless invisible collisions. Sometimes chaos is testimony. Even dust motes in sunlight can inspire the right questions. Now there is another hidden motion with profound importance: electrical current. When you charge a phone, switch on a lamp, or commit to watching one more documentary than planned, electrons move through circuits. Charges respond to electric fields. Energy transfers through networks. Modern civilization depends heavily on guided microscopic motion. Cities glow because particles cooperate. Now let us be careful with language. When we say atoms move, we often use classical shorthand for phenomena described more accurately through quantum mechanics and statistical physics. The microscopic world can be counterintuitive. Yet the broad truth remains: matter is active internally, not inert in the everyday sense. The table is busy, the air is busy, your cells are busy, the stars are busy. Even vacuum in some quantum descriptions is not mere nothingness, but a state with structure and fluctuations. Nature seems reluctant to leave any level entirely empty or idle. Now why does all this hidden activity matter emotionally? Because many things that feel motionless in life are full of unseen progress. A person resting may be healing. A habit quietly repeated may be changing a future. A relationship with no dramatic announcements may be strengthening through small, consistent acts. A skill practiced invisibly may be taking root. Science repeatedly teaches that surface stillness can hide meaningful work. Your body understands this already. Muscles rebuild after rest. Memory consolidates after sleep. Calm often contains preparation. Now imagine if our senses revealed every microscopic motion directly. The room would seem like a hurricane of molecules. Your skin would register endless impacts. Solids would feel less solid. Air would appear crowded and frantic. A sip of water would become a torrent of interacting particles. It would be accurate in one sense and unusable in another. So the brain gives us a stable summary world. Useful, not complete. That kindness lets us function. We can sit quietly in a room that is, in truth, immensely active. There is wisdom there too. Sometimes peace is not the absence of activity. It is activity organized so well that it feels calm. The universe seems to know this deeply. As you rest tonight, atoms in the mattress vibrate gently. Air molecules cross the room in restless zigzags. Cells in your body continue their careful labor. Neurons shift chemistry and charge. The planet turns. The galaxy moves. Large motions continue above you. Small motions continue within you. By now, motion seems to be everywhere we look. Planets orbit. Galaxies drift. Earth spins. Air molecules collide. Atoms vibrate. Cells exchange matter and energy. Even objects that appear still are usually busy beneath the surface. That naturally leads to a quiet but important question. Why does movement continue at all? Why does the universe not simply slow down, settle, and stop? In ordinary life, stopping seems common. A rolling ball loses speed. A bicycle coast ends. A swinging pendulum gradually comes to rest. Your enthusiasm for answering emails may decline sharply by mid-afternoon. Everyday experience suggests motion fades unless something keeps pushing. So it is tempting to imagine that all movement requires constant feeding, and that without fresh effort the universe should eventually become still. Yet this intuition is shaped by friction. Friction is so common in daily life that we mistake it for a universal rule. The floor resists shoes, air resists moving cars, bearings resist wheels, water resists paddles, hinges complain, fabrics drag, carpets oppose ambition. Energy is constantly being transferred into heat, sound, deformation, and turbulence. Because of this, moving objects around us often slow down. But slowing is not the same as motion being unnatural. It usually means motion is being redirected. That distinction matters enormously. When a ball rolls across the floor and stops, its movement has not been annihilated into philosophical nothingness. Energy is spread into tiny heating of the floor, slight sound waves, internal flexing of materials, microscopic vibrations, and surrounding air motion. The visible motion ended. The energy changed form. This is one of the deepest principles in physics. Energy is conserved. In a closed system, energy is not created from nothing or destroyed into nothing. It transforms. It can become motion, heat, light, chemical potential, electrical energy, gravitational energy, and other forms. But the accounting remains. Nature is an excellent bookkeeper. Now let us step into space where friction is scarce. If a spacecraft fires engines and then turns them off, it does not immediately stop. It continues coasting. No invisible cosmic hand reaches out to say, momentum has expired. With little resistance, motion persists. This surprised people historically because daily life rarely offers such clean examples. On Earth, everything rubs against something. Galileo helped recognize this by imagining motion with reduced friction, and Isaac Newton later formalized it. An object in motion remains in motion at constant velocity unless acted upon by a net external force. That is inertia. Movement does not need constant encouragement. It often needs only the absence of interference. There is something unexpectedly reassuring in that. Sometimes progress continues not because of endless pushing, but because enough obstacles have been removed. Now let us ask a subtler question. If energy is conserved, why do some motions obviously become less useful? Why does a spinning top slow? Why does hot tea cool? Why does a neat room tend toward mysterious clutter? Because while total energy is conserved, the quality and concentration of energy matter. A spinning wheel has organized energy easy to use for motion. Warm tea has thermal energy concentrated relative to cooler air. As systems interact, energy tends to spread out into less organized forms. This is closely tied to entropy, which we will visit more deeply later. For now, think of it this way. Movement may not vanish, but it can become dispersed. A marching band can become a crowd. The people remain energetic, but the pattern changes. Now consider a pendulum clock. At first it swings visibly. Over time, air resistance and internal friction reduce the amplitude. Unless wound or powered, it stops. Yet the stopping happened through transfer. Tiny warming of pivots, air movement, sound, material strain. No magic theft occurred, just redistribution. Likewise, when you rub your hands together quickly, friction turns organized motion into heat you can feel. Movement became warmth. That same principle scales upward. Meteorites entering atmospheres heat intensely because kinetic energy converts through collisions with air. Car brakes warm during stopping because motion becomes heat. Electrical resistance in wires warms devices because charge motion transfers energy into lattice vibrations. Everywhere, energy changes costume. Now let us return to the cosmos. Stars shine because gravitational energy helped compress gas until fusion began. In the core of the Sun, hydrogen nuclei combine into helium, releasing energy. That energy moves outward through radiation and convection, eventually leaving as sunlight. The warmth on your face from morning light began in nuclear processes sustained by gravity and pressure. Again, movement and energy are intertwined. Particles move faster in hot plasma. Radiation streams outward. Convection circulates. Even starlight is energy in transit. Planets orbit because gravitational potential energy and kinetic energy balance in elegant ways. A planet falling inward gains speed. Climbing outward costs speed. Stable orbits continually trade between position and motion. Nature often prefers exchange over stasis. Now consider water behind a dam. It stores gravitational potential energy because of height. Release it, and water flows downward, turning turbines. Height becomes motion. Motion becomes electricity. Stretch a bowstring. Elastic potential energy becomes arrow speed. Charge a battery. Chemical arrangements become electrical energy later. Eat dinner. Chemical energy becomes warmth, movement, thought, regrettable dancing, or a nap. Life itself runs on conversions. Now here's a common misunderstanding worth easing gently. People often say we use up energy. In ordinary language, that is fine. In strict physics, we usually mean we convert concentrated, useful energy into more dispersed forms. Gasoline in a car does not vanish. Its stored chemical energy becomes motion, heat, sound, exhaust chemistry, and a little unnecessary revving in parking areas. The phrase used up often means less available for the purpose we wanted. This matters because it reveals why movement cannot just stop universally. Energy remains in circulation, though changing forms continuously. Now, can all motion eventually cease in some local sense? Certainly. A book can come to rest on a shelf. A ball can stop rolling. You can finally stop pacing after remembering why you entered the kitchen. But even then, microscopic motion remains unless at impossible perfect zero temperature. Atoms vibrate. Air molecules strike surfaces. Earth rotates. Earth orbits. The galaxy moves. Rest is usually local and approximate. Stillness is negotiated, not absolute. Now let us visit temperature again, because it beautifully links motion and energy. In gases, temperature relates to average kinetic energy of particles. Hotter gas means faster random molecular motion on average. Cooler gas means slower. So heating air in a room increases hidden movement. Cooling reduces it. This is why thermal expansion occurs. Faster microscopic motion often increases average spacing in materials. Warm rails expand. Warm lids loosen. Warm bread smells particularly persuasive. Small motion creates familiar consequences. Now imagine the early universe. Extremely hot, dense, energetic. Particles colliding constantly. As expansion proceeded, energy densities changed, temperatures fell, structures formed. The universe did not transition from motionless to moving. It evolved through changing forms of motion and energy from the beginning. This reverses intuition again. We often imagine rest as the default state and activity as interruption. Physics frequently suggests dynamic processes are fundamental, while apparent rest is temporary balance. Now let us make this personal for a moment. Your body cannot just stop while alive. Your heart circulates blood. Lungs exchange gases. Cells maintain gradients. Neurons transmit signals. Muscles preserve posture even in quiet sitting. Digestion proceeds with or without applause. Sleep continues regulation and repair. To be alive is to sustain organized flows. Fatigue is not proof of failure. It is evidence that management of energy matters. Nature budgets carefully. You're not lazy because you need rest. Complex systems require maintenance. Now there is another elegant principle, momentum. Even when energy transforms, moving systems carry momentum that changes only through interactions. This is why billiard balls transfer motion, rockets recoil when expelling exhaust, and skaters glide after pushing off. The universe respects continuity. Things do not arbitrarily halt between one moment and the next. Change comes through causes and exchanges. This reliability is what makes engineering possible, prediction possible, and catching a ball sometimes possible. Now imagine a universe where motion could simply disappear for no reason. Planets might stop mid-orbit. Cars might freeze on roads. Waves might halt halfway to shore. Conversations could end after 3 words, which to be fair might improve some meetings. But such a universe would be chaotic in the wrong way. Laws would fail, patterns would fail, stability would fail. Instead, we inhabit a cosmos where movement changes through consistent rules. That consistency is a form of kindness. Now, none of this means motion lasts forever in the same form. Stars exhaust fuel, rotations slow through tides, orbits evolve, heat spreads, structures transform. But transformation is not nothingness. The river changes shape while water continues. That may be one reason science can feel calming. It reveals continuity beneath appearances. What seems like ending is often conversion. What seems like stopping is often redistribution. What seems lost may be diffused. Now, as you rest tonight, your body is warm because microscopic motion continues. The room's air drifts in invisible currents. Earth spins without needing to be wound. Earth orbits without needing daily permission. Sunlight stored in plants and food became your present metabolism. You're sitting inside ancient chains of energy transfer still unfolding. Imagine sliding a puck across perfectly smooth ice. It leaves your hand, glides forward, and keeps going far longer than intuition expects. There is something almost magical about that kind of motion. No engine, no visible effort, no tiny helper hidden inside pushing it onward. Just movement continuing because movement had already begun. That simple image leads us into one of the most powerful ideas in physics. The universe is reluctant to slow things down. Not emotionally reluctant, of course. The cosmos has never sent an apology note for friction. But in a deep mechanical sense, nature does not casually cancel motion. Objects tend to keep doing what they are already doing unless something interacts with them. This tendency is tied to momentum. Momentum is the quantity of motion carried by an object. In basic terms, it depends on mass and velocity. A heavier thing moving at a given speed has more momentum than a lighter thing at the same speed. A faster thing has more momentum than a slower version of itself. That is why catching a slowly tossed pillow feels different from catching a thrown bowling ball. One is a domestic event. The other is a lesson in applied mathematics. Momentum matters because it is conserved in isolated systems. When objects interact, total momentum is accounted for. It can transfer, redistribute, or change direction. But it does not simply evaporate because circumstances became inconvenient. Nature keeps records. We have met this theme before with energy, and here it returns in another form. The universe is not fond of arbitrary disappearance. Motion must go somewhere, be balanced somehow, or continue until acted upon. That is why movement so often persists. Take a car rolling on a flat road in neutral. It gradually slows because of tyre friction, air resistance, internal mechanical losses, and tiny inefficiencies everywhere. Yet if those resistances were absent, the car would continue moving. Daily life trains us badly on this point because Earth is full of resistance. Floors rub, air pushes back, wheels deform, bearings warm, fabrics drag, and doors insist on being dramatic. We mistake these constant interruptions for proof that stopping is natural. In truth, slowing usually means interaction. No interaction, no reason to stop. This insight became clearer through the work of Galileo Galilei and later Isaac Newton. Newton's first law states that an object at rest remains at rest, and an object in motion remains in motion at constant velocity unless acted upon by a net external force. That statement sounds tidy and academic. It is also revolutionary. It means motion is not a condition that constantly needs justification. Often, change in motion needs justification. The default is continuity. A planet already moving keeps moving. A spacecraft already travelling keeps travelling. A skater already gliding keeps gliding, until ice, air, or a wall begins negotiations. There is something philosophically satisfying there. Persistence may be more fundamental than interruption. Now let us look upward. Earth circles the Sun because of gravity and momentum together. Gravity bends Earth's path inward. Momentum carries Earth forward. Remove momentum, and Earth would fall inward. Remove gravity, and Earth would move off in a straight line. Combine them, an orbit appears. The Moon does the same around Earth. Satellites do the same around planets. Many graceful patterns in astronomy are balances between pull and persistence. Without momentum, gravity would collapse systems quickly. Without gravity, momentum would disperse them. Together they compose curves. This principle extends to galaxies. Stars orbit galactic centers because they possess motion while responding to the galaxy's gravitational field. Clusters of galaxies evolve under the same broad logic. Even matter gathering in the early universe did not simply plunge straight inward from every direction. Existing motions shaped disks, spirals, rotations, and long-lived structures. Momentum helps the universe avoid becoming a heap. Now consider collisions because they reveal momentum beautifully. When one billiard ball strikes another, momentum transfers. One slows, the other speeds up. Directions change according to geometry and energy losses. Similar principles govern everything from car crashes to molecules colliding in gas to stars interacting gravitationally over time. At a rocket launch, momentum appears in dramatic style. A rocket moves upward because exhaust gases are expelled downward at high speed. The rocket and exhaust together conserve momentum. Nothing magical pushes against empty space. The rocket pushes mass one way and recoils the other. This surprises many people because it feels as though motion requires something external to push against. It does not. Internal exchanges can reorganize momentum within a system. Nature remains perfectly happy with that arrangement. Now let us move smaller. Air pressure in a room arises from molecules bouncing off surfaces and transferring momentum in countless collisions. Every wall around you is being tapped continuously by invisible molecular traffic. Pressure feels static only because the impacts average smoothly. Again, calm emerges from busy accounting. A warm room contains faster molecules on average than a cold one. Their collisions transfer more momentum and energy. Temperature and momentum intertwine at microscopic scales. You're surrounded by hidden negotiations. Now think about walking. It feels simple enough. Yet every step involves momentum exchange with Earth. You push backward on the ground. The ground pushes you forward. Because Earth is massive, its recoil is tiny beyond practical notice. Yours is useful. Even sitting down on a chair includes momentum management. You lower yourself. Muscles break descent. Cushions compress. Forces distribute, and comfort is achieved if engineering has been kind. Daily life is full of momentum quietly resolved. Now there is a cosmic elegance to all this. Once the early universe began expanding and matter started moving under gravity, much of what followed inherited those motions. Clouds retained angular momentum and formed spinning disks. Galaxies developed rotational structure. Planetary systems formed from moving material, not static ingredients. The present carries the past forward physically. Momentum is memory written in motion. That phrase should be handled carefully, but it captures something true. Current movement often tells us about earlier conditions. Astronomers infer unseen masses from orbital speeds. They reconstruct collisions from debris trajectories. They estimate galactic histories from stellar motions. A system's present momentum contains clues to its formation. Watch how things move, and history leaks out. Now let us talk about why slowing still happens so often around us. Suppose you roll a ball across carpet. The carpet fibers deform. The ball deforms slightly. Internal friction converts organized motion into heat. Air resists. Tiny sounds emerge. Motion disperses into many channels. The ball stops. Yet from a conservation perspective, stopping is misleading language. Visible rolling stopped. The energy and momentum were redistributed through interactions with Earth and surroundings. Momentum can be transferred to the planet itself, though imperceptibly tiny amounts because Earth is enormous. Push a skateboard backward and you move forward. Throw a ball while on a chair with wheels and you roll back. Systems always keep score. The reason Earth seems unaffected by your steps is scale, not exemption. Now imagine outer space again. A probe launched decades ago can continue travelling because little opposes it. The Voyager 1 and Voyager 2 continue outward largely on the strength of momentum acquired long ago, guided by gravity assists and initial propulsion. Machines can coast for generations. That is almost poetic, though also engineering. There is another side to momentum that humans know emotionally. Habits have momentum. Projects have momentum. Arguments, unfortunately, have momentum. So do recoveries, learning curves, routines, and friendships, built through repeated contact. Once patterns begin, they often continue unless acted upon by meaningful forces. Physics does not dictate psychology, but the analogy is useful. Starting can be difficult. Continuing may become easier once movement exists. Nature seems to reward beginnings. Now consider sports. A moving truck is harder to stop than a bicycle because of greater mass and momentum. A baseball pitched quickly can sting because changing its momentum rapidly requires force. Martial arts, gymnastics, diving, and dance all rely on managing momentum through timing and body position. Grace often means excellent accounting. The same is true of celestial mechanics. Space agencies plan flybys that borrow momentum from planets. A spacecraft passing Jupiter can gain speed relative to the Sun, while Jupiter loses an immeasurably tiny amount of orbital momentum. Everyone remains balanced. The universe permits clever bargains. Now there is an important nuance. Relativity refines momentum at high speeds and extreme conditions. When objects move near light speed, classical formulas need updating. Momentum still exists and remains fundamental, but the details follow Einstein rather than Newton. Science often keeps principles while improving language. That should encourage us. Being corrected does not mean being discarded. Now, why call this the universe's reluctance to slow down? Because slowing is never just a spontaneous mood. It requires interaction, resistance, exchange, a force or process altering motion. Left alone, systems continue according to the momentum they carry. That means the cosmos is not constantly restarting everything each second. Much of reality is inherited continuation. The Earth keeps orbiting because yesterday's motion became today's motion. The moon continues because previous moments hand the path forward. You breathe in rhythms built from prior breaths, prior heartbeats, prior metabolism, prior sunlight stored in food, prior stellar energy forged long ago. Continuity reaches farther than we notice. As you rest now, the planet beneath you keeps turning partly because nothing substantial has stopped it. Earth orbits because momentum and gravity remain in their long conversation. The solar system moves through the Milky Way. The galaxy itself continues through larger structures. You're being carried by ancient persistence. Stand on a railway platform and watch a train pass. From your point of view, the train moves quickly while the station remains still. Step inside the carriage, sit by the window, and something curious happens. Your coffee rests on the table. Your bag sits beside you. The seat appears steady. Inside that moving train, many things now seem motionless, while the countryside glides by instead. Both experiences feel correct, and that is because they are. Motion depends on where you stand. This idea is so common in daily life that we rarely stop to admire it. Yet it is one of the deepest truths in physics. There is no universal viewpoint handed out by nature from which all movement is measured absolutely. Instead, motion is described relative to a frame of reference. A frame of reference is simply the perspective from which positions, speeds, and events are measured. It might be a person on a platform, a passenger in a train, someone standing on Earth, or an astronaut floating near a spacecraft. Change the frame, and the description changes. The train example is gentle enough, but the principle reaches from ordinary life to the structure of space-time itself. If you toss a ball straight upward while seated on a smoothly moving train, the ball rises and falls back into your hand. To you, it travelled vertically. To someone outside watching from the platform, the ball followed a curved path forward while rising and falling, because it kept the train's horizontal motion while also moving up and down. One ball, two valid descriptions. Physics is comfortable with this. Now imagine Earth. To someone standing in a garden, a tree may appear still. Yet relative to the Sun, that same tree is rotating with Earth and orbiting through space. Relative to the centre of the Milky Way, it is moving far faster still. Relative to distant galaxies, another speed again may be assigned depending on the chosen coordinates. So when we say something is still, we usually mean still relative to nearby surroundings. This is practical and useful. It is not absolute. That distinction quietly reshaped science. For centuries, many thinkers imagined there must be a preferred cosmic rest frame. Surely somewhere there existed a true unmoving background against which all motion could be judged. It is a natural intuition. Rooms feel still. Ground feels still. Certainty feels appealing. But experiments and theory steadily undermined that hope. The laws of mechanics already suggested something surprising. If you're inside a smoothly moving ship with no windows, many experiments behave the same as they would in a stationary room. Toss a ball, walk across the floor, pour tea carefully. Nothing inside reveals constant straight-line motion by itself. Galileo Galilei emphasized this relativity of uniform motion long before modern technology confirmed it repeatedly. You cannot detect steady motion merely by existing inside it without looking outward or feeling acceleration. That is why Earth's movement can be so easy to ignore. We move smoothly enough that local life proceeds normally. Now let us step into the 19th century. Physicists studying light expected that, like sound travelling through air, light might move through some invisible medium often called the luminiferous ether. If such a medium existed, Earth moving through it should create detectable differences in measured light speed depending on direction. The famous Michelson-Morley experiment sought this effect. It did not find it. The expected ether wind refused to appear. This puzzle helped prepare the ground for a profound shift. Then came Albert Einstein in 1905 with special relativity. Einstein proposed two bold principles. First, the laws of physics are the same in all inertial frames, meaning frames moving at constant velocity relative to one another. Second, the speed of light in vacuum is the same for all observers, regardless of their relative motion. That second statement sounds simple until you sit with it. If a car drives toward a thrown ball, the ball's speed relative to the car changes in ordinary mechanics. But light behaves differently. Everyone measuring it in vacuum gets the same value. To make this true, space and time themselves must adjust, and they do. Special relativity tells us that observers moving relative to one another can disagree about lengths, durations, and simultaneity, while agreeing on the underlying laws. Time can dilate. Length can contract along the direction of motion. Events judged simultaneous in one frame may not be simultaneous in another. This is not philosophical moodiness. It is measurable physics. Atomic clocks flown on aircraft, precise particle experiments, and technologies such as GPS all confirm relativistic effects. Now, before anyone worries, you do not notice dramatic time dilation walking to the kitchen, because everyday speeds are tiny compared with the speed of light. Relativity matters most strongly at high speeds, high precision, or strong gravity. Still, the principle is universal. Even if the effects are small, motion remains frame-dependent. Let us take simultaneity, one of the strangest parts. Suppose lightning strikes both ends of a train at the same time according to someone standing on the platform. A passenger moving with the train may see the flash from the front later than the flash from the rear because they move toward one pulse and away from the other. Each observer can consistently analyze the event according to relativity. There is no single cosmic now shared identically by all observers everywhere. That realization changes more than equations. It changes intuition. We live as though the present moment is globally obvious. Physics suggests the universe is subtler. Now let us add gravity. Einstein's later theory, general relativity, describes gravity as curvature of space-time caused by mass and energy. Objects move along paths shaped by that curvature. This also affects motion and measurement. A clock deeper in Earth's gravity runs slightly slower than one higher up. GPS satellites must correct for both their speed and their altitude relative to Earth's gravitational field. Without relativity, navigation errors would accumulate rapidly. Your map works partly because space-time is taken seriously, a charmingly modern dependency. Now think again about standing still. If you stand on Earth, you feel stationary. Yet Earth rotates, orbits the Sun, and moves with the solar system through the Milky Way. There is no contradiction, because standing still means at rest relative to Earth's surface. Likewise, someone seated beside you is still relative to you, but moving rapidly relative to the Sun. Both are true. Truth in physics often comes with stated conditions. This is healthy. Many arguments in life arise because people forget to specify their frame of reference. A city apartment is small relative to a mansion, spacious relative to a suitcase, expensive relative to reason, and cozy relative to honesty. Scale and frame matter everywhere. Now let us consider momentum and energy briefly. These quantities also depend on frame. A parked car has zero kinetic energy relative to the road, but large kinetic energy relative to a fast-passing train observer. Neither description is mistaken. Measurements belong to contexts. What remains invariant are deeper relationships, not every surface number. That pattern appears repeatedly in science. Descriptions vary, underlying laws endure. Now there is emotional comfort hidden here. You may sometimes feel behind, ahead, stuck, rushing, drifting, late, early, or uncertain. Much of that language depends on comparison frames chosen consciously or unconsciously. Physics cannot solve human worries directly, but it does whisper a useful caution. Perspective shapes judgment. Where you stand changes what motion looks like. Now back to the cosmos. Astronomers often choose convenient reference frames, Earth-centered for local observations, Sun-centered for planetary motion, galaxy-centered for some problems, cosmic microwave background frames for large-scale cosmology. No frame is morally superior. Some are simply more useful for certain questions. This is practical wisdom. Choose the viewpoint that clarifies the problem. Now imagine two spacecraft passing each other smoothly in deep space. Each crew can reasonably regard themselves as at rest while the other moves. There is no hidden label saying who is really moving in the special relativistic sense. Only relative velocity between them matters. That can feel unsettling at first because humans often want a final privileged perspective. Yet there is elegance in its absence. The universe does not require a throne. Now, acceleration is different. If one craft fires engines, occupants feel thrust. If a train brakes sharply, passengers lean. If a lift begins rising, bodies notice. Acceleration leaves local traces. Constant velocity often does not. This is why smooth travel feels restful while jerky travel feels personal. Your inner ear is an excellent physicist with limited patience. Now consider light from distant galaxies. As space expands, wavelengths stretch, producing cosmological redshift. This resembles motion-related redshift but arises from expanding spacetime itself. Once again, where and how you define the frame matters. Cosmic motion is richer than simple objects crossing static space. And that returns us to our theme. Why is everything moving? Part of the answer is that motion is not a single absolute property waiting to be stamped on objects. It is relational. It depends on comparisons, coordinates, observers, and geometry. A thing can be still here, swift there, and differently measured elsewhere without contradiction. That may seem complicated. It is also liberating. reality can be consistent without being simplistic. You are motionless relative to your bed, moving with Earth relative to the Sun, moving with the Sun relative to the galaxy, and part of larger motions beyond easy imagination. All of those statements can be true together. You're not trapped in contradiction. You're nested in frames. Take two identical clocks. Place one on a quiet table in a peaceful room. Put the other aboard a spacecraft travelling at enormous speed, then bring it home again. Set them side by side. If the journey were fast enough, the clocks would disagree. One would have measured less time. That sounds like the opening of a clever riddle or the sort of prank scientists play when given funding. Yet it is real physics. Motion does not merely change where things are. Under the right conditions, motion changes how time passes. This is one of the most astonishing discoveries humanity has made. Time is not separate from movement. Time is shaped by it. For much of history, people imagined time as universal. Minutes were minutes everywhere. Seconds ticked identically for everyone. The universe was thought to possess one grand invisible clock, keeping perfect rhythm for all things alike. It was a sensible idea. If two people meet at noon, noon feels shared. If bread bakes for 30 minutes seems stable enough. If a kettle takes too long, it does so democratically. Daily life supports the intuition that time flows equally for all. Then physics looked more carefully. In the early 20th century, Albert Einstein developed special relativity, revealing that measurements of time depend on motion between observers. The faster you move relative to someone else, the slower your clock runs relative to theirs. This effect is called time dilation. It does not mean your wristwatch becomes lazy or your calendar loses motivation. It means time itself, as measured along your path through space-time, differs from that measured by another observer moving differently. That sentence deserves gentleness, because it is strange. Let us begin with why this happens. Einstein started from two principles. First, the laws of physics are the same in all inertial frames, meaning frames moving steadily relative to one another. Second, the speed of light in vacuum is the same for all observers. No matter how fast you chase a beam of light, you still measure light moving at the same speed. That constancy forces space and time to adjust. If observers moving differently must agree on light speed, then they cannot all agree on distances and durations in the old absolute sense. So time stretches, lengths contract. Simultaneity becomes relative. The universe preserves deeper consistency by sacrificing simpler intuition. Now imagine a light clock. Picture two mirrors facing each other with a pulse of light bouncing between them. Each bounce marks a tick. If the clock rests beside you, the light travels straight up and down between mirrors. If that same clock moves sideways rapidly relative to you, the light follows a diagonal zigzag path because the mirrors move during the bounce. A longer path for light, yet light speed remains constant. Therefore each tick takes longer from your perspective. The moving clock runs slow relative to you. This simple thought experiment captures the essence of time dilation beautifully. Motion changes the geometry of measurement. Now, before anyone worries about tomorrow's commute, these effects are tiny at everyday speeds. Walking to the kitchen will not noticeably preserve your youth, though it may improve snacks access. Driving to work will not create dramatic age differences between passengers and pedestrians. Relativity becomes significant at speeds approaching the speed of light, or in extremely precise measurements. Still, the principle is universal. Small effects remain real effects, and we have measured them many times. Atomic clocks flown on airplanes differ slightly from clocks left on Earth. Fast-moving unstable particles created in accelerators survive longer than expected from their own frame, because their internal processes run slower relative to laboratory observers. This is not metaphor. Nature signs the paperwork repeatedly. Now let us meet the famous twin paradox. Two twins begin the same age. One remains on Earth, the other travels in a spacecraft near light speed and later returns. The travelling twin has aged less. This is often called a paradox, but it is really a teaching device. The travelling twin changes frames by accelerating during turnaround, so the situations are not perfectly symmetric. The result follows relativity consistently, move differently through space-time, age differently. That idea has permanently entered science fiction, and occasionally family arguments. Now, motion is only half the story. Gravity also shapes time. According to general relativity, clocks deeper in gravitational fields tick more slowly than clocks farther away. A clock on Earth's surface runs slightly slower than one higher above Earth. A clock near a massive object such as a neutron star or black hole would run dramatically slower compared with one far away. This phenomenon is gravitational time dilation. So both speed and gravity influence time. Motion bends it one way, mass curves space-time and bends it another. Together they create a universe where time is local, not universal. Now consider Global Positioning System, GPS. GPS satellites orbit Earth at high speed and high altitude. Because of their motion, their clocks run slightly slower than clocks on Earth. Because they are farther from Earth's gravity, their clocks also run slightly faster than clocks on Earth. Both effects must be calculated carefully. Without relativistic corrections, navigation errors would grow quickly, and your phone might confidently direct you into lakes, hedges, or emotional uncertainty. Modern convenience depends partly on accepting that time is flexible. There is something delightful about that. Now let us return to the deeper picture. Relativity combines space and time into space-time. Instead of thinking of time as a separate river flowing everywhere the same way, physics treats time as one dimension woven with the three dimensions of space. Different observers slice space-time differently depending on motion. That is why they can disagree about elapsed time or simultaneity, while agreeing on the laws governing events. Each observer traces a path through space-time called a world line. The amount of time experienced along that path is sometimes called proper time. Not all paths accumulate equal time between the same events. That sounds technical. It is also profound. Life is not merely movement through space while time happens separately. Your motion partly determines your experience duration. Now, in everyday human terms, we need not become alarmed. Your evening tea will not age differently enough from you to cause social strain. Your cat's sprint across the room will not create a measurable identity crisis. Yet the conceptual shift matters enormously. Time is not a background stage manager. It participates. Now there is a philosophical softness hidden in this science. We often treat time as a tyrant, fixed, uniform, marching sternly onward. Relativity reveals something gentler and stranger. Time is relational. Context matters. Paths matter. Conditions matter. That does not remove deadlines, sadly, but it does make the cosmos less rigid than once imagined. Now think again about motion everywhere. Earth rotates. Earth orbits the Sun. The Sun orbits the Milky Way. The galaxy moves through larger structures. You're already in motion through multiple layers. Those motions are far too modest relative to light speed to matter much for your personal clock. But they remind us that stillness was never the default anyway. We are always travelling. We simply travel together smoothly enough not to notice. Now let us visit black holes briefly, because they are where time becomes especially dramatic. Near a black hole, gravity is so intense that clocks close to it run much slower relative to clocks far away. In principle, someone hovering near the edge for a while could return to find far more time passed elsewhere. Black holes turn relativity from subtle correction into spectacle. They are nature's way of underlining equations. Now none of this means time is an illusion in the lazy sense sometimes claimed. Clocks tick, bodies age, events occur. Rather it means time is not one size fits all. It is woven into the physical circumstances of observers. Reality keeps time personally. Now there is also comfort in this. When we say a moment felt long or short, we speak psychologically. Science usually separates feelings from equations. Yet here physics itself says duration can genuinely depend on path and condition. Experience and universe are not always strangers. The language differs, but both know that context matters. Now picture two travellers taking different roads between the same cities, one winding through hills, one direct through plains. They do not accumulate the same mileage. Relativity suggests something analogous for time. Different journeys through spacetime need not accumulate the same duration. Again, nature prefers geometry over simplicity. As you rest tonight, your body's clocks continue quietly. Heartbeat rhythms, circadian cycles, cellular chemistry. Above you, satellites adjust for relativistic effects. Distant stars move under curved space-time. Light from remote galaxies crosses expanding space for ages before reaching eyes and telescopes. Every second around you is more flexible than it appears. Open a neatly organized drawer, leave it alone for long enough, and sooner or later reality begins improvising. Socks migrate. Receipts appear from forgotten centuries. Charges knot themselves with private determination. The arrangement that once looked efficient softens into something more interpretive. This small domestic mystery points toward one of the most important ideas in physics. Things tend to spread out. Order often requires maintenance. Disorder arrives with less supervision. The scientific word most associated with this tendency is entropy. Entropy is famous for sounding intimidating and then behaving more simply than expected. It is often described as a measure of disorder, though more carefully it relates to the number of microscopic arrangements compatible with a system's visible state. That sentence can feel dense, so let us unpack it gently. Imagine a deck of cards sorted perfectly by suit and rank. There are many ways to shuffle cards into mixed arrangements, but very few ways to keep them in that exact ordered pattern. Mixed states are vastly more numerous than tidy states. Left to random shuffling, mixed outcomes are more likely. Not because the universe dislikes neatness, because there are more ways to be messy than precise. Entropy often increases for similar reasons. Systems naturally move towards states that can happen in many more microscopic ways. Now, why does this matter for motion? Because many motions we observe are driven by imbalances that tend to spread out over time. Heat flows from hot objects to cool ones, gas expands to fill containers, perfume diffuses across a room, pressure differences drive winds. Water runs downhill, distributing gravitational potential energy. Concentrations smooth out. Gradients relax. Motion frequently occurs because something uneven becomes more even. That is entropy in action. Let us begin with a warm mug of tea on a cool table. At first, the tea contains thermal energy concentrated in faster-moving molecules. The surrounding air and cup are cooler. Molecules collide, transfer energy, and over time temperatures approach equilibrium. The tea cools. The room warms by a tiny amount. Microscopic motion spreads. You experience this as disappointment if you waited too long. Physics experiences it as statistical inevitability. Now reverse the process in imagination. Could a lukewarm mug spontaneously gather thermal energy from the room and become piping hot while the room cools? The laws of motion at the microscopic level do not strictly forbid every individual collision pattern needed, but the odds are so fantastically tiny that for practical purposes it does not happen. Entropy is deeply tied to probability. The forward direction of many everyday processes is simply the overwhelmingly likely direction. This is one reason time feels directional. Eggs scramble, but do not unscramble. Smoke disperses but does not politely return to the candle. Ice melts in warm water rather than assembling itself from puddles. We remember the past, not the future. The microscopic laws can often run both ways mathematically, yet large systems overwhelmingly move toward higher entropy states. That gives time an arrow. Now consider a perfume bottle opened in one corner of a room. At first, scent molecules are concentrated locally. Soon they spread everywhere through random motion and collisions. No supervisor assigns routes. No tiny committee votes on corners. The molecules simply move and collide. There are far more mixed arrangements than concentrated ones. So diffusion happens naturally. This principle powers many processes in life. Oxygen diffuses into blood. Carbon dioxide diffuses out. Nutrients cross membranes. Weather redistributes heat. Even social gatherings sometimes resemble particles seeking available space with mixed success. Now let us look upward. Stars exist in a fascinating tension with entropy. Gravity pulls gas inward, apparently creating order by concentrating matter. Yet in doing so, gravitational collapse heats matter, radiates energy outward, and increases total entropy overall. A star forms as gas contracts, then shines by converting nuclear fuel and sending energy into surrounding space. Local structure can emerge while total entropy still rises. This is crucial. Entropy increasing does not mean everything becomes instantly featureless chaos. It means the total number of accessible microstates grows, often while temporary organized structures appear. Life itself depends on this. Earth receives concentrated low-entropy energy from the Sun and radiates more dispersed infrared energy back into space. That flow allows local pockets of complexity, weather, ecosystems, brains, bread, and bedtime documentaries. You're not a violation of entropy. You're a beautiful temporary arrangement sustained by energy flow. That is far nicer. Now many people hear disorder and imagine mess in the moral sense. Physics does not judge your desk. Entropy is not scolding clutter. It is describing statistical tendency. A tidy room can have low entropy in some respects, but also many hidden complexities. A messy room can contain excellent retrieval systems known only to its owner. Science remains diplomatically silent. What matters physically is how many microscopic configurations correspond to a visible macrostate. Still, the drawer example remains emotionally persuasive. Now, think of a gas in one half of a box separated by a partition. Remove the partition. Gas spreads to fill the whole box. Molecules now have more available positions. Entropy increases. Could all molecules later gather spontaneously back into one half? Again, not impossible by pure law, but absurdly improbable for large numbers. Probability becomes destiny at scale. This is why we trust some things to happen one way, not because nature signed a contract, but because the odds are overwhelming. Now let us connect entropy to motion more directly. Why does wind blow? Because uneven heating creates pressure differences. Warm air rises, cooler air moves, circulation forms, energy redistributes. Why do ocean currents flow? Because temperature, salinity, rotation and gravity create gradients seeking new balance. Why does weather exist? Because Earth receives uneven solar heating while rotating under fluid atmospheres and oceans. Much motion on Earth is the planet processing imbalances. Nature dislikes gradients only in the sense that gradients invite dynamics. Now consider your own body. You maintain internal order constantly. Cells repair damage. Membranes preserve concentration differences. Temperature stays regulated. Food supplies chemical energy that helps sustain these organized states. Without continual energy intake and waste export, biological order decays. Life is active resistance to equilibrium. That sounds dramatic, but it is practical. You eat to keep structure going. You sleep to restore systems. You breathe to support energy pathways. Rest is maintenance, not laziness. A valuable sentence. Now there is a subtle beauty here. Entropy explains why perpetual motion machines of the impossible sort do not work. You cannot endlessly extract useful work from a system without losses and dispersal. Real processes leak into heat, friction, noise, turbulence, imperfections. Nature charges operating costs. Engineers spend careers reducing them, never eliminating them entirely. Now let us return to time. Why do we remember yesterday and not tomorrow? Memories require physical traces formed in brains and records formed in matter. Those traces are created through processes that increase entropy. The past leaves marks because events have happened and spread consequences forward. The future has not yet done that, so even psychology may be linked to thermodynamic direction. That is wonderfully strange. Now imagine filming a glass falling and shattering, then playing the film backward. Backward motion looks absurd because shards leaping together into a perfect glass would represent an extreme decrease in entropy. We instantly detect it as unnatural. Our intuition about time's direction is trained by entropy-rich experience. Now none of this means entropy is an enemy. Without it, there would be no heat engines, no metabolism, no weather, no mixing of nutrients, no flowing rivers, no stars aging, no cosmic evolution. Change often requires gradients relaxing. Entropy is not merely decay, it is transformation with statistical direction. There is another comforting way to say it. The universe moves because differences exist. Hot and cold, high and low, dense and sparse, charged and uncharged, compressed and expanded. Where differences appear, flows can happen. Where flows happen, work can happen. Where work can happen, complexity can arise. Many beautiful things begin as imbalances. Now, on the larger scales, the early universe seems to have begun in an unusually low entropy state, though understanding exactly why remains one of cosmology's deepest questions. From that condition, structure and history unfolded. We are living inside a long consequence of initial improbability. That should feel remarkable because it is. Now let us make this personal one last time. If parts of life feel messy, it may help to remember that maintenance is real work. Order does not persist by accident. Homes, bodies, friendships, gardens, and minds often require steady energy input. The universe is not singling you out. Even stars must burn fuel to remain stars. Look at a spiral galaxy in a photograph and it can seem almost decorative. A bright central glow, curving arms, dust lanes folded through starlight, something balanced, elegant, nearly still. The sort of image that belongs on a wall, in a textbook, or on the cover of a very serious album. But behind that graceful appearance lies a puzzle. Galaxies move in ways the visible universe alone struggles to explain. Stars orbit galactic centers, gas clouds circle, clusters of galaxies hold together. Great streams of matter flow across cosmic structures, and when astronomers add up all the stars, dust, glowing gas, planets, and ordinary matter we can detect, there often does not seem to be enough gravity to account for what is happening. Something unseen appears to be helping. We call it dark matter. Now, the name can sound dramatic, as though it lurks in alleys wearing a cloak. In reality, dark here means it does not emit, absorb, or reflect light in ways we readily observe. It is not dark because it is evil. It is dark because it is difficult, and difficult things have kept science busy for centuries. Let us begin with galaxies. If you spin a merry-go-round, objects farther from the centre usually move faster in terms of linear speed to complete each turn in the same time. In the solar system, planets farther from the Sun move more slowly because most of the mass is concentrated in the Sun. So when astronomers first considered galaxies, they expected stars far from galactic centres to slow down in ways similar to planets orbiting a concentrated mass. Instead, many galaxies showed something surprising. Outer stars often move faster than expected, or at least not nearly as slowly as visible matter alone predicts. These measurements are called galaxy rotation curves. Instead of dropping off sharply with distance, the curves remain relatively flat. Something beyond visible stars and gas seems to provide additional mass spread throughout and around the galaxy. That unseen mass strengthens gravity, allowing faster orbital speeds. One of the key figures in demonstrating this problem was Vera Rubin, whose work on galactic rotation helped make dark matter a central topic in modern astrophysics. By watching stars move, she helped reveal matter we could not see. motion became evidence. That theme returns again and again in astronomy. Now imagine standing at the edge of a city at night. You see lit windows, roads, and street lamps. You estimate the population only from visible lights. But much of the city may be inside dark buildings, asleep underground, or hidden from your angle. Your estimate would miss something important. Likewise, when we look at galaxies, visible light may not tell the whole mass story. Now widen the view to galaxy clusters. Clusters are enormous collections of galaxies bound by gravity. Their member galaxies move rapidly. Hot gas fills space between them. If only visible matter existed, many clusters should not remain bound as observed. This issue was noticed early by Fritz Zwicky in the 1930s while studying the Coma cluster. He inferred missing mass from galaxy motions long before dark matter became mainstream. His conclusions were not fully embraced immediately, which is a common scientific tradition whenever someone is early. Later evidence accumulated. Now we also detect dark matter indirectly through gravitational lensing. According to Albert Einstein's general relativity, mass bends spacetime, and light follows those curves. Massive objects can distort, magnify, or duplicate the light of more distant galaxies behind them. By measuring how light is bent, astronomers can map mass distributions, including mass that emits no light. Sometimes the lensing maps show much more mass than visible matter provides. Again, something unseen appears present. The universe keeps leaving fingerprints without showing the hand. Now perhaps the most famous example is the Bullet cluster. Two galaxy clusters collided. Ordinary hot gas, which interacts electromagnetically, slowed and heated during the collision. But much of the inferred mass from gravitational lensing passed through more cleanly, offset from the gas. This separation between visible baryonic matter and gravitational mass is often cited as strong evidence that dark matter is a real component rather than merely a misunderstanding of gas behavior. In short, when the clusters crashed, the glowing matter and the gravity did not stay perfectly together. That is extremely interesting. Now, what might dark matter be? Honest answer, we do not know yet. Many candidates have been proposed. WIMPs, or weakly interacting massive particles, were long popular possibilities. Axions, hypothetical lightweight particles, are another candidate. Sterile neutrinos and other new particles have also been considered. Experiments underground, in space and at particle accelerators continue searching. So far, no definitive detection has settled the matter. Science sometimes spends decades knocking politely on the right door. Now there is another possibility. Perhaps gravity itself behaves differently on large scales than we currently think. Modified gravity theories attempt to explain some observations without dark matter particles. These models can be insightful and worth studying, though many researchers find the total body of evidence still favours some form of dark matter. The conversation remains active. That is healthy science. Evidence first, pride later. Now let us return to motion itself. Dark matter seems especially important because it may have helped structure form early in the universe. Ordinary matter interacts with light, which in the early universe made it harder to clump immediately. Dark matter, interacting weakly if at all with radiation, could begin gathering gravitationally earlier. Its halos may have provided scaffolding into which gas later fell, cooling into stars and galaxies. If so, many luminous structures we admire were built inside invisible frameworks. That is a striking thought. The visible universe may be architecture furnished inside hidden foundations. Now consider our own Milky Way. The stars you see in the night sky occupy only part of its total mass budget. The Milky Way likely sits inside a much larger dark matter halo, extending far beyond the bright disk. Our solar system orbits not just through starlight, gas and dust, but through a region influenced by matter we cannot see directly. You may currently be surrounded by dark matter particles passing through Earth and through you in enormous numbers each second, if particle models are correct. No need for alarm. Their interactions with ordinary matter would be extremely weak, which is precisely why detection is difficult. It is the most polite traffic imaginable. Now, there is something emotionally grounding about this mystery. We often mistake visibility for completeness. If we cannot see something, we may assume it is unimportant or absent. Science repeatedly corrects that instinct. Air is invisible yet essential. Gravity is invisible yet decisive. Magnetic fields are invisible yet practical. Dark matter, if our interpretation is right, may outweigh ordinary matter by a large factor in the cosmos. Much of reality does not audition for our senses. Now think of rivers at night. You may not see the current clearly, but leaves drifting, reflections bending, and branches moving reveal flow. In the same way, astronomers often infer unseen cosmic currents from what visible matter does. Stars moving too quickly, galaxies lensing background light, clusters staying bound, patterns in the cosmic microwave background, large-scale structure statistics. The invisible announces itself through consequences. Now let us zoom out further. Computer simulations, including dark matter, can reproduce web-like cosmic structure resembling what telescopes observe: filaments, nodes, clusters, and voids. Ordinary matter then falls into these gravitational wells, forming galaxies. The universe may have grown like dew collecting on hidden wireframes. Again, not literal but suggestive. Now, none of this means dark matter solves everything. We still do not know its composition. We still refine measurements. We still test alternatives. We still seek direct detection. Mystery remains. But mystery with evidence is different from mystery without clues. Here we have clues everywhere. Now there is a human parallel worth noticing. Many forces shaping life are not visible at first glance. Trust, stress, habits, grief, confidence, social norms, history. You may not see them directly, yet their effects move people profoundly. Astronomy teaches a similar humility. What is obvious is not always what is dominant. Now imagine looking at the night sky before modern science. You would see stars and darkness. Reasonably enough, you might think the bright parts were most of the story. Today we suspect the opposite in some sense. The luminous matter-making stars, planets, oceans, trees, and listeners may be only a minority of cosmic matter. We are made from the rarer visible ingredient, living inside a larger unseen framework. That does not make us lesser. It makes the universe richer. Stars continue their galactic orbits faster than visible mass alone suggests. Light from distant galaxies bends around hidden halos. Clusters hold together through gravity supplied partly by something not yet fully named in substance. Invisible structure guides visible motion. Set a book on a table, step back, and it seems the matter is settled. The book is not sliding, it is not bouncing, it is not orbiting visibly around the lamp. It appears to have reached the noble final state many objects seek in daily life, staying where it was put. We call this rest. We trust it instinctively. Yet after everything we have explored together, a fair question remains. Is anything ever truly still, or is stillness only a useful shortcut? A practical word for motion we no longer notice? The answer, as so often in physics, depends first on what we mean. If by still we mean not changing position relative to nearby surroundings, then yes, stillness is common. The book rests on the table. Your pillow rests beneath your head. A parked bicycle rests against a wall, hopefully more gracefully than usual. This local sense of rest is real and useful. Without it, shelves would be emotionally exhausting. But if by truly still we mean absolutely motionless in every possible sense, relative to all things, internally inactive, unchanged at every scale, then the concept becomes much harder to find. Perhaps impossible. Let us begin with the book. Relative to the table, it may be at rest. Relative to Earth's surface, it remains in one place. Yet Earth rotates. Earth orbits the Sun. The Sun moves through the Milky Way. The galaxy moves relative to neighbouring structures. Space itself expands on large scales. So the resting book is participating in several layers of motion already. It did nothing to earn this travel package. Now look inside the book. Its atoms vibrate. Molecules hold structure through electromagnetic interactions. Thermal motion persists. Electrons occupy quantum states. The paper exchanges heat slowly with surrounding air. Moisture content may change slightly over time. Gravity presses it into the table pushes back. Stillness, then, is not inactivity. It is stable arrangement. That distinction matters. Many things we call still are active systems whose changes cancel, balance, or remain too subtle to notice. A sleeping cat appears motionless while breathing, digesting, regulating temperature, dreaming, and maintaining the deepest confidence in the room. A mountain appears fixed while weathering, eroding, rising or sinking tectonically over geological time. A lake appears calm while currents circulate beneath the surface. Stillness often belongs to the eye, not the full reality. Now there is a deeper challenge. Motion is relative. To ask whether something moves, we usually ask compared with what. A passenger sitting quietly in a train is still relative to the seat, moving relative to the station, and differently described relative to the sun. There is no universal sticker reading actually motionless. Physics does not seem to provide a throne of absolute rest from which all movement is judged. This insight grew through the work of Galileo Galilei and later Albert Einstein. In modern physics, especially relativity, there is no preferred ordinary inertial frame declaring itself the final stationary perspective. Frames are chosen for usefulness, not for cosmic prestige. Now there is one interesting reference frame cosmologists sometimes mention: the frame in which the cosmic microwave background radiation appears most isotropic, meaning roughly the same in all directions. Relative to that frame, we can describe Earth and the Milky Way as moving with measurable velocities. This gives a convenient large-scale standard. But it is not absolute stillness in the old philosophical sense. It is a useful cosmological benchmark, not the universe handing us a gold medal for stopping. Now let us turn inward again. Could something become internally motionless? Temperature gives us a clue. In classical terms, cooling matter reduces microscopic motion. The colder a system becomes, the less thermal agitation remains. This leads toward absolute zero Kelvin, the lowest possible temperature in thermodynamics. Scientists can cool atoms astonishingly close to absolute zero using advanced techniques. At such temperatures, matter behaves in remarkable ways. Superconductivity, superfluidity, quantum condensates, and other phenomena emerge. Yet reaching absolute zero exactly appears forbidden by thermodynamic principles. One can approach indefinitely, but not fully arrive through finite processes. Nature allows nearing the frontier while keeping the gate closed. Even more intriguingly, quantum mechanics suggests that systems can retain zero-point energy, a kind of residual ground state activity. So the deepest calm may still not be classical total stillness. The universe remains subtly restless. Now think of a pendulum. Left alone in air, it slows and stops. This looks like motion ending entirely. But what happened? Energy transferred into air movement, sound, internal friction, and heat. The visible swing ceased because organized motion dispersed into less obvious forms. Again, stopping often means transformation. A rolling ball stops on carpet because motion became microscopic vibrations, heat, and tiny deformations. A cooling drink stops steaming dramatically because energy spread into the room. A battery dies because chemical potentials equilibrate. What vanishes from sight often survives as changed form. Now let us scale upward. Could an orbiting planet ever simply stop in space? Not without interaction. Momentum carries it onward unless gravity or another force alters the path. If Earth suddenly lost orbital motion, the results would be severe and unhelpful. Thankfully, physics does not casually permit such nonsense. Could a star stop shining? Yes, in the sense that fusion can end. But then the star transforms into a white dwarf, neutron star, black hole, or remnant cloud depending on mass. Motion, gravity, radiation, and matter continue in new arrangements. Could the universe itself stop evolving? That is a profound cosmological question. Expansion may continue, stars may fade over immense timescales, black holes may evaporate incredibly slowly through Hawking radiation. Matter may decay if certain theories are correct. Future scenarios include heat death, big rip possibilities, recollapse models, or other outcomes depending on cosmology. Some futures involve less usable energy and less dramatic structure, but even there, nothing happening can be misleading. Quantum processes, radiation, expansion, and statistical events may continue. Silence at one scale may hide activity at another. Now, there is a psychological side to this topic worth visiting gently. Humans often long for stillness. A still room, a still mind, a still weekend with no notifications. Yet complete stillness may not be what we truly seek. Usually we seek calm, not absence. Calm is different. Calm allows breathing, heartbeat, thought, safety, warmth, and subtle life. Calm is activity harmonized enough to feel restful. The ocean can be calm while waves continue softly. A person can be calm while emotions still exist. A body can be at rest while trillions of cells work faithfully. This mirrors physics beautifully. The universe rarely offers absolute stopping. It often offers balanced motion. Now consider meditation or quiet reflection. Thoughts may continue, sensations continue, breath continues, blood flows, time passes. The goal is seldom annihilation of process. It is a gentler relationship with process. Again, not stillness as emptiness, stillness as steadiness. Nature seems to prefer that definition too. Now let us revisit the sleeping cat, because it deserves another appearance. A cat in sunlight may look like a sculpture of contentment, yet ears flick to sound, whiskers sense air, metabolism runs, dreams likely involve impossible confidence. Paws twitch, chest rises and falls. Perfect stillness would be concerning. Tiny motions reassure us. Likewise with people. Breathing in sleep is movement. A pulse is movement. Warm skin indicates molecular motion. Signs of life are signs of ongoing flow. We should be grateful for motion. Now, there is another subtle truth. Even if absolute stillness existed somewhere, detection would be difficult. If you and everything around you shared exactly the same motion, no internal experiment might reveal it. Without contrast, movement hides. We know change through differences. This compared with that. Now compared with before. Here compared with there. Without relationships, stillness and motion blur conceptually. That alone hints the universe may be fundamentally relational, rather than built around fixed absolutes. Now imagine a hypothetical final frozen cosmos with no gradients, no usable energy differences, no structure changes of note. Even then, describing it would rely on laws and states, not on some simple word like stopped. Reality resists oversimplification to the end. So can anything ever truly stop? Locally, yes. Practically, often. Absolutely, perhaps not in the way intuition hopes. Objects come to rest relative to surroundings, systems reach equilibrium, motions damp out, temperatures equalize, patterns settle. But beneath and beyond those useful states, layers of motion usually remain. The book rests while Earth turns. The room is quiet while air molecules wander. The night is calm while the planet orbits. You are lying still while time carries chemistry forward. That is not disappointing. It is beautiful. Because it means peace does not require emptiness. Rest does not require the universe to freeze. Stillness can exist as a lived experience inside ongoing motion. As you settle more deeply now, your body continues its quiet work. Outside, stars move unnoticed. Galaxies turn. Space expands. Tiny particles interact. Nothing has entirely stopped, and yet this moment may feel still enough. Picture the night sky 1 trillion years from now. No city lights to compete with it. Perhaps no cities at all. Familiar constellations long since rearranged. The sun gone through its later transformations. Earth changed beyond recognition or absent entirely. The bright band of the Milky Way merged with Andromeda Galaxy into some larger, descendant galaxy with a new shape and no concern for our naming preferences. Would anything still be moving? After everything we have explored, it may be tempting to answer yes automatically. Motion seems woven into reality itself. Yet the deeper question is not merely whether something moves, but what kinds of motion remain available as the universe ages. Will there always be orbits, winds, stars, collisions, warmth, chemistry and flowing change? Or does the cosmos gradually spend its opportunities? To approach that question, we need to distinguish between motion and useful motion. A rock drifting through empty space moves. A photon crossing darkness moves. An atom vibrating faintly moves. But these are not the same as a planet with weather, a star with fusion, or an ecosystem powered by sunlight. The future of motion depends heavily on energy differences, structures and gradients that allow interesting things to happen, and those may not last forever. Let us begin with what observation suggests now. The universe is expanding, and that expansion appears to be accelerating. Evidence associated with distant supernova measurements and modern cosmology indicates some form of dark energy or equivalent effect influences large-scale dynamics. If that continues, distant galaxies beyond our local gravitationally bound region will recede farther and faster over time, not through ordinary engines, through expanding space itself. In the far future, observers in our merged local galaxy may see a darker sky. Many galaxies currently visible could drift beyond the observable horizon, their light no longer able to reach future civilizations. The universe may become lonelier from any local point of view. That is a sobering image, but loneliness in scale is not the same as emptiness in reality. Those galaxies would still exist elsewhere, continuing their own histories. Separation would grow, not total absence. Now let us think about stars. Stars shine because fusion converts lighter elements into heavier ones, releasing energy under the right conditions. But stars are not eternal, they consume fuel. Large stars burn quickly and die dramatically. Smaller stars burn slowly and steadily. Red dwarfs, the smallest common stars, can shine for trillions of years, far longer than the sun. So even after sun-like stars are gone, the cosmos may still contain many faint persistent stellar lights. Motion around those stars could continue. Planets orbiting, moons circling, debris drifting, perhaps life adapting if conditions permit. The universe has long patience when it chooses. Eventually, though, star formation is expected to decline. Galaxies use up or eject much of their cold gas, the raw material needed for new stars. Existing stars age. The brilliant era of abundant starlight fades. Astronomers sometimes describe our current time as living during a relatively lively stellar age. We arrived while the theatre was still bright. Now imagine much later eras. White dwarfs, neutron stars, black holes, brown dwarfs, and stellar remnants dominate. Fewer luminous stars remain. Orbits still exist. Gravity still operates. Objects still move. But the kinds of motion associated with vibrant new creation become rarer. A cemetery can contain movement, wind, footsteps, growing grass, but it differs from a playground. The future cosmos may keep moving while becoming quieter. Now, let us consider planets. Planetary systems evolve. Orbits can remain stable for immense times, though not always forever. Tidal interactions alter rotations. Stellar mass loss changes orbital distances. Close encounters may eject worlds. Collisions may occur over unimaginable spans. Nothing promises eternal neatness. Still, many systems may persist for astonishing durations. Motion can outlast brightness. Now comes one of the most famous long-term possibilities, heat death. Despite the dramatic name, heat death does not mean everything suddenly catches fire and files paperwork. It refers to a state where energy becomes so evenly spread that large-scale useful work becomes extremely difficult. Gradients vanish. Differences that power engines, weather, metabolism, and organized processes become scarce. Particles may still move. Radiation may still exist. Space may still expand. But the universe would lack many exploitable contrasts. No hot, stars beside cold space in the familiar way. No abundant free energy to build complexity easily. Motion remains, significance changes. Entropy has been preparing this conversation all along. Now there are other speculative futures. If dark energy strengthens over time in certain ways, a big rip scenario has been proposed, where expansion accelerates so extremely that galaxies, stars, planets, and eventually smaller structures are torn apart. Current evidence does not require this outcome, but it remains an explored possibility. Another possibility in older cosmological models was recollapse. Expansion halts and reverses into a big crunch. Present data make this less favoured under standard models, though cosmology continues refining itself. There are also cyclic and bounce models in which cosmic phases repeat or transition. Science remains open where evidence remains incomplete. Now let us visit black holes. Black holes may become central actors in very late cosmic eras. They can persist for immense times. Yet according to Stephen Hawking, black holes are not perfectly eternal. Quantum effects imply they may emit Hawking radiation and slowly evaporate. For stellar black holes, this timescale is absurdly long. For supermassive black holes, longer still beyond ordinary imagination, but not infinite. Even nature's sternest objects may eventually fade. That thought is strangely democratic. Now what about matter itself? Some grand unified theories have proposed proton decay, where ordinary matter could slowly transform over colossal timescales. This has not been observed, and protons may be stable. But if decay occurs, then even familiar matter is temporary on sufficiently long horizons. Atoms themselves would not keep their current form forever. Again, motion persists through transformation. Now, there is a subtle emotional trap here. When people hear of fading stars and cold futures, they often feel sadness as though the universe is ending tomorrow. But these timescales are so vast that language strains. Trillions, quadrillions, or vastly greater years exceed not only civilizations but likely many forms of imaginable continuity. We are not standing at the edge of a closing shop. We are early enough that stars still shine abundantly. We live during a rich interval. That can be received not as dread, but gratitude. Now there is another perspective. Why should permanence be required for meaning? A song matters though it ends. A season matters though it changes. A life matters though finite. Stars matter though temporary. Galaxies matter though evolving. Motion need not be eternal in its present form to be beautiful now. Physics and philosophy shake hands briefly there. Now, if the universe reaches a sparse late state, would motion literally cease? Probably not in any simple sense. Particles could still drift. Quantum fluctuations may still occur. Radiation may still cross space. Gravitational interactions among remnants may continue occasionally. Expansion itself may proceed. Even a nearly exhausted cosmos may retain activity at subtle levels. Stillness, once again, remains difficult to achieve absolutely. The universe seems more inclined toward thinning than freezing. Now think of a campfire. At first it blazes, sparks leap, logs crackle, warmth radiates strongly. Later it settles into embers. There is less drama, but not no activity. Heat remains, coals glow, tiny shifts continue, ash drifts. The far future universe may be more ember than blaze, different, not nothing. Now let us return to ourselves. Right now, Earth turns, oceans move, winds circulate, plants capture sunlight, hearts beat, cities glow, meteors burn, stars fuse hydrogen, galaxies rotate. New worlds likely form somewhere. We inhabit a period of abundant active contrast. That is rare enough to notice. Now, whether the universe keeps moving forever may depend on what counts as movement and what counts as forever. If you mean changing states, probably in some form for unimaginably long spans. If you mean rich structured activity like stars, weather and life, perhaps not indefinitely. If you mean perfect stillness, the cosmos has resisted that idea repeatedly. Now there is comfort in this too. Many people fear slowing down, aging, endings, transitions, yet the universe suggests a broader pattern. Forms change, processes continue differently, energy redistributes, stories transform, the blaze becomes embers, the river becomes mist, the tree becomes soil and forest. Nothing stays exactly as it was, yet continuity survives in altered language. The future is in no hurry to arrive. Stars still have work to do. Galaxies still turn. Space still stretches. Countless motions continue quietly beyond the window. Somewhere above you tonight, a star is moving. Perhaps many stars, perhaps more than can be counted by any one mind. They travel through the Milky Way in long, patient arcs. Far beyond them, galaxies turn inside clusters. Beyond those, space itself continues its quiet expansion. On smaller scales, planets orbit, moons circle, comets wander, particles collide, atoms vibrate, and light crosses distances so large that language becomes tired trying to follow. And here you are, still enough perhaps to rest. That contrast is one of the loveliest things we have discovered. The universe can be full of motion while offering moments of calm within it. Tonight we asked a simple question. Why is everything in the universe moving? Along the way, we found that stillness is often local, not absolute. A resting object may be travelling through larger frames. A quiet room may be full of microscopic activity. A sleeping body may be performing thousands of careful tasks without asking permission from consciousness. We learned that motion persists through momentum, that gravity bends paths into orbits, that rotation emerges from ancient imbalances, that time itself changes with speed and gravity, and that entropy gives direction to many processes by spreading differences outward. We found that galaxies move through hidden scaffolds of dark matter, that future ages of the cosmos may grow dimmer yet not entirely silent, and that perfect stillness remains strangely difficult to locate. Again and again, the universe answered with the same gentle theme. Change is normal, movement is common, continuity often hides beneath appearances. That may be useful knowledge beyond astronomy. Many days feel static while unseen progress continues. Healing can be invisible for a while. Learning can feel slow while roots are quietly forming. Relationships deepen through repeated small motions rather than dramatic declarations. Even rest can be active in ways we do not immediately notice. Science often teaches us outward truths that become inward comforts. Now consider your own position in all this. You may feel small compared with galaxies, clusters, and billions of years. That is understandable, but small is not the same as separate. The atoms in your body were forged in older stars. The oxygen you breathe was made in cosmic furnaces. The iron in your blood came from stellar deaths long before Earth existed. The sunlight that warmed today's streets began in nuclear reactions deep inside our sun. You're not outside the story looking in. You're one of the ways the story continues. The universe moved, changed, condensed, ignited, expanded, and evolved until eventually it could become aware enough to ask what it was doing. And tonight, that awareness happened to be lying under a blanket, perhaps adjusting a pillow, perhaps pretending not to be sleepy yet. There is something wonderfully human about that. Now think of motion in a softer sense. Your heart has kept time for you all day. Your lungs have risen and fallen faithfully. Thoughts have come and gone. Hours passed whether they felt quick or slow. The planet turned without asking anything of you. The night arrived on schedule. Soon morning will do the same. Much of life is carried forward by motions we do not need to personally manage. That can be reassuring. You do not spin Earth. You do not pull the moon. You do not ignite the sun each dawn. Some systems are already taking care of themselves. Your task tonight can be smaller. Breathe. Unclench the jaw if it has been holding meetings. Let the shoulders soften. Allow the mattress or chair beneath you to do its ancient supportive work. There is no prize for remaining mentally busy. If thoughts are still moving, that is fine. Thoughts move. Minds wander. Brains replay awkward conversations from 2017 with baffling dedication. None of that disqualifies rest. You do not need inner perfect stillness any more than the universe does. You only need enough calm to drift. That may be the final lesson here. Peace is not the total absence of motion. Peace is motion gentle enough to live inside. A calm sea still moves. A forest at night still breathes and stirs. A sleeping person still dreams, heals, and circulates warmth. A quiet cosmos still expands, rotates, glows, and glides. Rest belongs comfortably within movement. So if the day felt hectic, if your thoughts have been loud, if life lately has seemed full of spinning responsibilities and orbits of obligation, remember this. Even the universe moves constantly without panic. It turns in vast silence. It changes without rushing. It carries immense complexity with no visible strain. Perhaps we can borrow a little of that style. Let things move tonight without chasing each one. Let unfinished tasks remain in their current galaxy until tomorrow. Let questions wait in stable orbit. Let worries pass like distant traffic rather than parking beside the bed. You're allowed to pause even while everything else continues, and everything else will continue. Outside the window, Earth rotates steadily. Somewhere oceans shift with tides. Somewhere clouds gather. Somewhere dawn is beginning. Somewhere a telescope catches ancient light. Somewhere another person is also trying to sleep and losing politely. Across the cosmos, countless motions proceed with no need for your supervision. So you may rest now. You may simply be one calm passenger on a moving world, inside a moving solar system, inside a moving galaxy, inside an expanding universe, held by gravity, carried by momentum, warmed by old stars, surrounded by quiet processes older than memory. And if sleep is approaching, let it come the same way many beautiful things in nature arrive, gradually, softly, without announcement. Thank you for drifting through the universe with me tonight. Until next time, rest well.